All right, I can't remember who goes first. Is it me? All right. Good afternoon, everybody. This is Marcus Hawkins with the Organization of MISO States. I want to first off thank NARUC, NASEO, and especially the DOE's Grid Mod Lab for pulling together this great training that we have over the next 3 days. I'm really looking forward to it. Looking at the agenda, there's just such a great group of experts and very timely topics that will be of benefit, I know, to OMS members and NARUC members alike. And so just want to set the stage a little bit. In the MISO region, there's a lot of different activities going on at the state level related to distribution system planning, DERs, and the like. And OMS has been trying to serve as the platform, not only connecting those activities at the state level, but also connecting the dots between distribution systems and MISO and the wholesale level. And so since the last time this training was conducted in 2018 in the MISO region, OMS has issued 2 sets of joint priorities with MISO related to DER. And we've worked to iron out some of those very complicated coordination issues between the distribution and transmission systems. And so I'm really looking forward to the training because it really helps us speak the language of the distribution system and understand some of the finer details associated with that coordination. So that's all for me. Really looking forward to the training, and thanks again to all of the co-hosts for putting together such an amazing event. So thanks.
Thanks, Marcus. This is Kerry Worthington from the National Association of Regulatory Utility Commissioners. We would really like to thank the U.S. Department of Energy for their sponsorship of today's program. And I would like to thank on our staff, Dominic Liberatore, for his tremendous help with bringing this together. As I go through my thanks again to Kirsten, Verclas, and Rodney Stewart at NASEO. Thank you to OMS President Matthew Sugar and Executive Director Marcus Hawkins. And a special thanks to Lisa and the full training team. On a personal note, this is one of my top 3 favorite events of the year. Please don't make me choose, but it does bridge engineering and policy in a way directly relevant to utility commissioners and energy offices. So thank you all for being here and taking the time to attend this training. Please also thank your fellow regions for supporting this initiative. Over the years, we have worked with DOE to ensure that each region has content unique to your needs. At the end of each training, we send out an evaluation. We take those evaluations very seriously, and the comments from those evaluations have directly shaped future trainings. The NARUC Center for Partnerships and Innovation is offering a certificate of completion if you are able to join us each day. We understand that these are quite challenging times, so if you miss a session, you will be able to see the recording on our NARUC CPI website. Along with your pre-training package, we included recordings from the March training, and trainings from today will be located on the same page. But today, the training is your time, so please ask questions directly to the experts and know that they are the ones who are advising the full industry. So if you'd like to practice at the moment, I will flip my slides so that you can see some of our logistics. Today's presentation is being recorded. The presentations are located on LBNL's website. We are using polls throughout the day. The individual responses will not be released. And I think I've covered everything else. So if you'd like to practice your chat, just say hello. And if you're not able to see your questions box, then go to the view tab or send one of us an email and we can help you out. So hopefully that covers it, and Kirsten from NASEO will pick it up. Thanks.
Thank you so much, Kerry. And I just wanted to, on behalf of NASEO, National Association of State Energy Officials, say welcome to you all to this training. We're very excited to be partnering with NARUC and OMS and LBNL. Again, on some of these regional trainings. We've done this before in person, now it's virtual, but I think you will still find it very enriching and enlightening and rewarding. We partner with NARUC a lot on these issues. We have another effort, the Comprehensive Electricity Planning Task Force, that we do together. We have the Grid Interactive Efficient Buildings Working Group, or GAB Working Group, as well as the working group on microgrids between the two organizations. So we're really pleased to continue this collaboration with LBNL and OMS and NARUC in this space. Kerry has already thanked DOE, but of course, on behalf of NASEO, I also want to thank DOE, especially Joe Paladino and Monica Newcomb. Office of Electricity and the Buildings Technology Office are great supporters of this effort, and really great to collaborate with you all again. We also wanted to say for the GAB working group, a really highly valued component is the provision of national lab technical assistance to the working group. And Lisa and Natalie from LBNL and Juliet Hormer from PNNL are really leading this effort. And so kudos to you all. I know our members really appreciate this. In terms of the Comprehensive Electricity Planning Task Force, we're kind of nearing the home stretch. We have another workshop in November, and we will continue the work until February when we release state action plans, so stay tuned for that. And with that, I would just like to turn it over to Joe for your remarks. Thank you.
Kirsten, thank you very much. I really appreciate it. I want to thank you all for being here, and I hope you're all doing well during this very strange coronavirus times, and I hope we get through this process well. I want to really thank Lisa Schwartz for organizing this. Lisa, you've done a great job, but I also want to thank you, Kirsten, at NASEO, Marcus Hawkins at MISO, and Kerry Worthington at NARUC for your support and assistance. It's really the collaboration, and the partnership has been great. And I want to thank all of the speakers as well today and through the next 3 days. They've really spent a lot of time putting some great material together. And I also want to mention Monica Newcomb, who is my co-worker here. We both, at DOE, we both lead this project and reach out to the folks that I just mentioned in order to make it happen. I particularly like the agenda and hope you find it both interesting and useful. We wanted to provide some foundational information today on distribution system operations, but we also want to be able to provide some information on needed coordination between the transmission, distribution, and customer domains. That coordination is becoming increasingly important there, and we also want to talk about cybersecurity. Tomorrow, we're going to launch into integrated planning. And we want to really address two key questions. One, how do we incorporate grid modernization into our integrated planning processes? And two, how do we incorporate resilience into our integrated planning processes? And obviously, both of these considerations are highly coupled, and whole systems resilience planning is now just evolving. So there are a lot of questions as to how to move forward in an organized way in that arena. We're hoping that the discussion with respect to integrated planning is going to help you develop guidance to utilities with respect to their planning processes, as well as help you better critique their filings and plans. And the major question that we have, that I think all of us are facing right now is really, what is a rational pathway for building out needed functional capabilities, and what type of grid structure and architecture do we really have to consider as we try to develop a more advanced grid, obviously within the time constraints that we're looking at. And then finally, on the last day, we're looking at the evolving grid edge. And obviously, there's a lot of organic growth there, but for us, I think we have to figure out how we can shape it to, in effect, an orderly transition to a more advanced grid. And with that, we may have missed things, probably have. We've been doing this for the past several years. But really, your input is important. Let us know what we missed, what we can do better. And again, thank you all for being here. And Lisa, take it away. Thank you.
Thanks, Joe. I'm Lisa Schwartz with Berkeley Lab. Welcome to the 6th in a series of regional trainings for states on distribution system planning. Thanks for joining. Berkeley Lab leads the training for U.S. Department of Energy's Grid Modernization Lab Consortium. And our two funders, you just heard from Joe from DOE's Office of Electricity. Also, Monica Newcomb is our program manager from the Building Technologies Office. I want to thank our longstanding partners. We absolutely could not do it without you, NARUC, NASEO, and our sister labs, Pacific Northwest National Lab, Lawrence Livermore, and National Renewable Energy Lab. And thanks, Marcus, our regional partner, Organization of MISO States. We also want to thank our elite group of trainers. They're drawn largely from all of the grid modernization projects that DOE is funding. And we also have brought in outside technical experts for some of the sessions. Everyone's sharing their expertise and research in various areas in distribution systems and planning because they think this training is really important. And we really enjoy this group effort. So as Joe said, we've divided this training into 3 modules. And today, we're starting with a series of foundational sessions on distribution systems and operations. So first is a nuts and bolts overview. We'll talk about power system fundamentals, electricity system equipment, sensors and communications, and how they all work. And we'll talk about integration, management, and control of distributed energy resources, including the different types, issues related to their integration, and management and control. And we're also going to talk about controllable loads in buildings and control strategies. Then we'll take a break, and after that, we'll talk about the operational coordination between transmission and distribution, and we'll end the day with a session on communications and sensors in the distribution system and cybersecurity. So all of these presentations are posted on the Berkeley Lab website. I just put the link in the chat box. The link is also in the email that NARUC sent you all last week. Most of the presentations include slides in the very back with questions that states can ask. So what that's about is, these are questions that you could ask utilities or others that are involved in all of these various processes in relevant discussions you're having or in proceedings. And we also include resources for more information. We've just posted a list on our website that's a compiled list from all of these areas. So if you want to do some further reading or you need citations for work you're doing, please check there. So without further ado, let's get started with our overview of distribution system components, systems, and operations. Kevin?
Can you hear me now?
Yes, we can. Thank you.
Okay. How do I move the screens forward?
Dominic, I think, is controlling the slides.
Okay.
And so I think you
Kevin, no worries. We got control of the slides.
I do not appear to have control of them.
Kevin, we have a
Kevin, just
whole
say
slide
next
deck.
slide.
Okay. So I'll just say next slide when it comes to it. So I've broken this presentation into 3 parts. The goal of this presentation is to really talk about the fundamentals of electric power systems. The idea being that before you can start to envision what a future advanced edge-based, edge-enabled system is going to look like, you have to know the nuts and bolts and the fundamental underlying operational principles so that you can meet those as constraints. Because we've seen before that if you try to suppose a future without a fundamental understanding of how things operate, you can end up with solutions that don't make sense. So to that end, I've broken this into 3 parts, starting with the very fundamental, what is an electric distribution system, then focusing on some of the key pieces of equipment, and then finally talking about some of the basic control systems. This will just give you an overview of a very small portion of this, and it's the foundation for what we'll be looking at in later presentations. So next slide, please. So on this slide, it gives a little bit of a pictorial example of what is a distribution system. And so I like to use quite a few pictures in these, and there's a reason for that. If you ask a graduate student what is an electric distribution system, they'd give you an answer that looks like the picture on the right there. That picture on the right is a 1-line diagram in a distribution system planning software overlaid on Google Maps, and that's the way a planner would work at it. But when you're actually on the ground, you start to see the equipment that's at the left. the various pieces of equipment that exist in substations out in the field. And these are the devices that each of them serves a critical purpose. If they fail, typically that means there'll be a service interruption. And there's different ways to accomplish the roles that they fill. And it's good to understand what these are and what they appear to look like. Next slide, please. So within North America, the characteristics of a modern system. We use what's called a 4-wire unbalanced system. What this means is that we have 3 conductors that provide power and a neutral line. And I'll talk about that a little bit more in detail as we go further. In North America, we use 60 hertz. Voltages at the distribution level are typically less than 50,000 volts. More like 12,000 is much more common. Power levels, when you're talking distribution level equipment, less than 100 megawatts. And for a distribution circuit, power only goes less than 20 miles. There are exceptions, but these are good rules of thumb. We use a combination of overhead and underground lines here in North America. And for the most part, power is supplied from the sub-transmission systems. These are the bulk power systems that bring power into the region. Distribution circuits are almost always operated radially. What this means is that there is a single path of power to flow from the substation to each house. That's a very cost-effective way to do it, but there are some reliability issues because if you have a break in there, there's no power. But these can be rerouted manually and sometimes automatically, which I'll talk about later. At the distribution level, these systems were historically designed not to have any generation. However, this is increasing. We know in areas such as the Carolinas, Hawaii, California, and others, we're seeing a lot of solar generation go on, and that's fundamentally changing the characteristics. When you look at the operational characteristics, utilities in North America tend to be regulated, where you have enforced requirements, regulated rates of return, and so it's not the Wild West in a business sense. Things are very well thought out, and what that means is that the technical decisions are almost always driven by the regulatory environment. And we have different ownership models for public utilities or distribution utilities in North America. The investor owned, these are ones that they are publicly traded, owned, stock may exist. Municipal utilities, they're run by local cities. Typically their service territories can't extend outside that area. The rural co-ops, they exist in every state of the union and cover something on the order of 70% of the land mass. Historically, these serve just rural areas, but the name's misleading because in some cases they supply very urbanized areas. And then in some areas such as Washington, Oregon, we have public utility districts. Next slide, please. So an important part of the underlying operation is the type of current that we use in these systems. Many people are familiar with direct current. This is what you would get out of a battery. Basically, the current that flows out, or I should say the voltage that comes out of it over time is constant, more or less. This is what a lot of power electronics run on. This is what you'll see in your car battery. However, they don't interface very well with DC systems. And in this case, you require power electronic inverters to convert it to an alternating current, which we see on the right. In alternating current, the voltage 60 times a second will pass through zero in a sinusoidal form. The reason for this is that with alternating current, you can effectively use transformers to change the voltage. And this is what allows us to move power over long distances. And it's why AC originally won out over DC in the original Tesla Edison battle. With alternating current, you can generate power at around 20 to 30,000 volts. However, you can't move it very far at that voltage. So it's generated at that voltage, stepped up to 230, 500 in the Northeast, up to 765,000 volts. It can be transmitted long distances and then step down to distribution level voltages. That ability to cost effectively change the voltage is what makes alternating current such a common use today. With that said, power electronics are making the ability to transfer voltage more and more cost effective. So we'll see more direct current in the future. However, utilities will be primarily using alternating current for the foreseeable future. Next slide, please. Alternating current is typically produced by taking a coil, or I should say a magnet, or an energized coil. You connect it to a prime mover, whether it be a steam turbine, a gas engine, a hydroelectric turbine, and this rotates it around. This becomes your rotor. If you put coils next to that, you'll get an induced voltage in it in a sinusoidal form. And this is what produces a simple alternating voltage waveform. Folks may have done this in middle or high school where you can make these little type of generators. They're not very efficient with just one set of coils, but it's how historically we have produced the alternating current that is used in all of these systems. Next slide, please. Now, making just a single phase of power it's not very efficient from the geometry of machines. So what we've ended up doing is using a three-phase system. Pretty much every major generating station in North America will use three-phase generators. Smaller generators that you would use, say, on camping or as an emergency, maybe a single phase, but that's because that's the connection of the house. For our large central power plants, when we're dealing with tens, hundreds of megawatts, you'll have a three-phase system. As I said, the geometry of this makes it much more efficient. It was based on Nikola Tesla's patent of polyphase systems. Mathematically, he extended it to more than three phases, but what we find is that three phases really become a lot more efficient. Next slide should advance some animation. When you overlay these three phases, which is why we have three different conductors, you get this type of waveform here. It shows the three phases overlap with one another, but this would be on three different conductors. And that's why when you're driving down the road, you typically see three different wires on the overhead. Each of these will have one of the three phases, phase A, B, and C. And so the generators will connect to all three phases. Large loads can connect to three phases, but typically customers, residential type, will only connect to one. And so this gives us the voltage source, and that will cause current to flow. Next slide, please. When you start talking about the voltages and currents, the next question is the different types of power. And this is a common thing that you'll hear folks in the utility realm talk about, is that there's not just one form of power. And what I mean by that is when you have a voltage that's moving in a sinusoidal form, the current will flow, but it may not flow exactly what's called in phase with the voltage. And what I mean by that is we can see on this figure right here where the current and voltage are out of phase. You can see that when the voltage is at zero, current is still flowing in the system. And conversely, there's times when there's no current flowing, but there's voltage applied. This is called a phase shift, and various elements in a power system can cause that. If everything is just resistive like space heaters, this will be in phase, but because we have other elements in the system, such as inductors and capacitors, we'll get this phase shift where current will either lead or lag the voltage. And this results in different types of power. So first is the active power, and the physics definition of this, it's power, it's going to be consumed to do work or consumed work in the physical sense. And so this could be heating something up, moving an object. This is actually what is useful to us, and it's the component of voltage and current that are in phase with one another. The reactive power, this is the power that is consumed to maintain, establish and collapse electric and magnetic fields in the system on your inductors and capacitors, and it is represented by the component of the voltage and current that are out of phase with one another. And then finally, apparent power. This is the power that's measured by taking instantaneous measurements of your conductors. If I measure the magnitude of voltage and measure the current. Next slide, please. These three can be related to one another, and these become very important concepts when you're looking at how you rate the various pieces of electrical equipment. While the active power, P, may be what we really want, we know that there is some amount of Q, the reactive power, that also ends up flowing in the system. And so as a result, what you see is that the apparent power, S, it's the hypotenuse of P and Q. P and Q are at right angles to one another. And so where this matters is the amount of current that actually has to flow down the conductors. It's based on S, which is the apparent power. So what we see here is that while we may only want the active power, P, we have to supply some reactive power, and in the process of that draws more current down the lines, which heat things up. And so the result is either you need to have larger, more efficient equipment, or you have to look at how that's going to impact the lifetime of that equipment. So it becomes a bit of a trade-off. When you see about when you talk about the different equipment in electric power systems, they have multiple ratings. Typically, things like transformers will be represented in apparent power as either kVA or MVA, being kilo or million, and because really what you're looking at is the thermal ability for that to carry. However, the distribution engineers will be going in and looking at how much active power do I have to provide to the customers, what elements are going to be consuming reactive power, and how do I manage that? And that becomes a really big part of distribution system operations, is managing these three different types of power and their impact on voltage. Next slide, please. And that brings us to the second part, where we're going to go in and start looking at some of the key pieces of equipment in electric distribution systems. Next slide, please. The most important part of a distribution system starts with the distribution substation. For most distribution circuits, this is going to be the source of power that steps down power from either the transmission or sub-transmission system. So something on the order of 100 to 200,000 volts, possibly up to 230 or 500. And it will step it down with a substation transformer to voltages that are typically less than 50,000 volts. The most common voltage in North America is 12.47 kV, but there are a number of other voltages used: 13.2, 13.8, 24.9, 34.5. The trade-off is that the higher the voltage, it allows you to move power more efficiently over distance. However, it requires larger, more expensive equipment. And so this is really the big trade-off that you see in picking these voltages. Now, the challenge is that once you pick the voltage, all of the distribution system equipment uses that. And so if you decide to change the voltage over time, that requires changing out all of the equipment. That can be a very expensive and time-consuming process. I live in Seattle, which historically had a legacy 4.2 kV system, very low voltage, which required a lot of substations. But many years ago, they switched to a 26 kV system. That changeover has been taking well over 20 years because of the life cycle of equipment. So the voltage is a very important aspect of this. Next slide, please. Within the transformer, the single most important piece of equipment are the step-down transformers. These are large pieces of equipment that are designed to operate for 30 plus years. I've seen units in operation for over 50 years. Their primary function is to take the incoming power from the sub-transmission or transmission system, step it down to the lower voltage, and supply that out to the distribution circuits that head out into the system. The number one threat to these devices is heat. As you load them higher or put large spikes of power through them, that heating will degrade the internal electrical windings inside, and that'll reduce their lifetime. And so a lot of the operations around power systems are maintaining voltage, but also looking at what is the loading on the transformers and making sure they stay within their normal operating realm. You can see that these are actually pretty active devices in that the coils themselves are static, but some of these, such as the upper right hand, it's an interior building transformer. The exterior ones can have anything from passive cooling to forced fans to spray cooling. There's a lot of different ancillary systems that are designed to help these operate. Next slide, please. Once you leave the substation, there's a large amount of equipment out in the field, and really this is the vast majority of the distribution level equipment. This includes everything from the overhead conductors, which in the upper left hand we can see an example of two three-phase circuits overbuilt, one on top of the other. They will have a fourth common neutral down below them. It's just not shown in there. These are the overhead versions of it, but you'll also have transformers. Typically the customer service transformer, an example of that shown in the lower right, its role is to step it down to the 120, 240 voltage that we use. But there are other pieces of equipment such as voltage control devices, regulators, capacitors, and protection systems. These are all needed to maintain the normal operating parameters of the distribution system and to protect it from credible events such as lines or trees landing on lines, animals, cars that strike the poles and drop them, and things of that type. And so there's a large amount of equipment out there, and replacing it, once again, takes a long time because this equipment is designed to stay in place for a very long time. Next slide, please. Next part is to talk a little bit about how are all of these what are some of the basic control systems that can be used to operate this equipment. While much of this equipment exists out in the field, we're seeing a lot of modernization across utilities to start to look at how you can control it more efficiently. Historically, distribution systems were operated where you would build them out for maximum peak load, and then they would passively operate on their own. This was efficient as long as systems were overbuilt, people weren't worried about too much equipment being put in the field, and we didn't have a lot of active generation sources out there. As that's changing, utilities are adapting to look at different control mechanisms for how you would maintain normal operations. What we have here on the left-hand side is a picture of a distribution control center, a very traditional looking setup, and on the right-hand side is a picture of a more modern microgrid control setup. Next slide, please. The distribution control center, this is where utilities control their systems from. And this doesn't look like the big movie boards where you have a perfect map of everything going on. There's 100% accurate situational awareness. For a small utility, this may be nothing more than a laptop sitting in a closet. As you go to the larger utilities, they will in fact have big one-line mimic boards on the wall, many of them electronic, that'll give them some operational visibility into what's going on. And so they can see what the current status of the system is. However, the level of automation is somewhat limited, and most of an operator's work is really monitoring phone calls and coordinating operations with the field crews. There are some operations that they can take, especially with self-healing systems and some of the automation, but the vast majority of their work is what's called switch management work. Now, there are some remote pieces of information available, and these typically use a supervisory control and data acquisition, or SCADA system. These systems have been around for decades, and they're commonly used in power systems as well as oil and natural gas and other areas, but they are specifically designed to be able to read information from remote points in the field, dispatch control signals, and they are kind of the basic communication and control systems that utilities can use. These in themselves do not have a lot of advanced functionality, and they are brought together with more advanced systems such as distribution management systems, outage management systems, self-healing systems, and they can work together to implement more complicated functions within the system. Next slide, please. One of the basic functions that is examined is voltage control. Voltage control is probably the single most important operational aspect after making sure the system isn't overloaded that utilities have to worry about. In North America, the most commonly used standard is the ANSI C84.1. Most public utility regulators, they will go through and select this as the standard, and what it does is basically say, here's the range that it should remain within, and it's typically 120 volts up to 126 and down to 114, so plus or minus 5%. This standard on its own does not have any legal standing until a regulatory body sets it as the standard. And this is the voltage as measured at the customer meter. Now, I mentioned on the 120 volt scale, but really single phase residential houses receive 120, 240. So this can be scaled to the 240 as well. There is also another range B, which can be used under other ranges if there's an abnormal situation. This is once again up to the discretion of the Utility Commission. Next slide, please. When you look at an operational distribution system, it is almost always maintained within the range A limits of ANSI. The traditional way this is done is you take the voltage at the head of the distribution feeder or circuit, which is the substation, and they set it at the high end of the ANSI band, typically around 125 volts. And then the voltage tends to drop as it goes down the circuit because of all of the loads on there. Now, in a system where the power all flows from the substation to the end, that makes sense. You have a consistent drop of voltage the entire time. But it will vary how much it drops over the course of the day. And in this figure, you can see two different traces where you have the end of feeder voltage at minimum load and peak load. At the peak load, the highest load of the day, you see the voltage is brought down a lot more than it is during the peak load. And this is also, should be kept in mind, this is a conceptual drawing of an idealized single line going out. in reality, distribution circuits snake out in many different directions. So it's not as easy as a simple profile like this, but for a conceptual understanding, you can see how these are operated. Next slide, please. For situations where the voltage drop can become too high, utilities will deploy what are called voltage regulators. These are smaller transformers that are designed to be able to regulate their output voltage within a range. And so these are electromechanical devices, and they can be referred to as tapping up or tapping down. And what we see here is an example of two different tap settings, where the dotted line is a lower voltage tap setting, where it's set at just above 120 volts, and the second one is set at 126 volts. And so you can see in this case, you can move the voltage of the head of the feeder up and down, which will affect the voltage down the entire system. That level of flexibility allows you to accommodate for changes of, as the load changes in the day, you can go ahead and change your tap positions so that customers don't see the voltage drifting over the full range of the day. By actively tapping throughout the course of the day, you can keep the voltage in a much more narrow contained band. And for most utilities, you can even see this in your house. If you go put a meter to the outlet, it'll only vary a little bit. Now, this can depend on where you live. If you live in an urban area with a strong system, you may not see much voltage variation. If you're in a very rural community at the end of a circuit, it potentially could change quite a bit. Next slide, please. Here's another example of putting a regulator further out of the substation, because sometimes you can have a situation where even if you move the voltage all the way at the head of the feeder to the top end, you still may violate the low end by the end of the circuit. And so in this case, we see an example of a voltage regulator that was put out in the end of the field, where the voltage drops down and then it taps back up and then it starts to drop again. And so in this way, it allows you to you can put multiple regulators on there to extend the length of a circuit. And so this also allows you to go further, and it provides for higher level of regulation. Now, this is one of the technologies. You could also go out there and replace all the conductors, so there's less of a voltage drop, but that's a very large and expensive trade-off. And so these are the type of things that distribution engineers look at, is the trade-off between the different solutions that they have. Next slide, please. Another solution for regulating voltage are what are referred to as shunt capacitors. A voltage regulator is designed to be a small transformer that actively changes the voltage up or down, typically plus or minus 16 positions. It can work in almost any location. But going back to that power triangle that we saw earlier with reactive power, we know that we primarily want to deliver active power. If you only deliver active power, or P, that will reduce the current flowing down the system. However, we know that many loads, such as motors, some power electronics, will draw reactive power. And so one option is that instead of providing the reactive power all the way from the substation, shunt capacitors can be put out on the circuit near the points of the reactive power load, and these will have the net effect of reducing the current that has to come from the substation and raising voltage a little bit. So shunt capacitors, we see these often near industrial areas where you have large motor loads, sometimes where there's irrigation pumps. Sometimes they're even just used on long rural lines to compensate for some of the inductance of the system. And also rural lines tend to have more pump loads on them. Here below, we see another example of the type of curve that you can have. And basically, the shunt capacitor just kind of moves up the entire thing a little bit. Now, shunt capacitors can be put in different ways. They can either be fused directly into the system. So if you expect there's always a need for reactive power, they can do that. But then they can also be put in with switches so that they can be turned on and off at different times. And so this allows for, once again, a more flexible system. Next slide, please. Now, for many utilities, they'll deploy both voltage regulators and shunt capacitors, and they're operated independently. However, there is a technology referred to as Volt-VAR Optimization, and its goal is to actively coordinate the operation of both the voltage regulators and the shunt capacitors. And this is done to optimize the system. And so what it does is it tends to flatten the voltage profile across the entire distribution circuit, pushes it down to the low end of the acceptable band, and this has the effect of reducing the overall energy consumption. And so it makes the system operate more efficiently. And it's been well shown that if you operate on the low end of that band, loads will still provide the same quality of service, they just operate more efficiently. And so this is an example of one of the newer type of technologies. I should caveat newer because Volt-VAR optimization in various forms has been around for 30+ years, although it's becoming much more advanced these days because we have better communication systems. The SCADA is much better. The control systems are a lot better, and so is the computing power. So there's a lot of schemes out there for how can you optimize this information. And so I'm showing on the right-hand side a very simple example of a substation transformer with 3 distribution circuits that's coordinating the operation of 4 voltage regulators and 4 shunt capacitors. And it has some end-of-line measurements. These are meters out there that can measure the point so they can determine how low should a lower voltage. This is what I would call a traditional voltage optimization scheme, and these have been around for probably 10 years commercially. But what we're starting to see a little bit more on the advanced product offerings and definitely in the research is people are looking at how can you tie in things such as advanced meter infrastructure. So how can you bring in the meter reads from the customers to this system? How can rooftop solar participate in this? How can electric vehicles participate in this? And so this is an example of where you can take a traditional function such as voltage control and voltage optimization and look at putting a lot of edge computing capability and power on the system and really changing the way you do a traditional function. And in the process, you unlock a lot of benefit. However, to do that properly, you have to understand that when you engage all of these new assets, how will they be interacting with the historical assets such as the voltage regulators and shunt capacitors? Because if not implemented properly, you can decrease the life of that equipment and in some cases damage it or even cause it to misoperate. So this is a good example of, as technology moves forward, you have to have a solid foundational understanding of the base system, what it is you're trying to achieve, and what the impacts of what you're doing may be. And not just the first order impacts, but the second order, so you can look for those unintended consequences. And those type of topics will be talked about extensively in the next presentations. Next slide. With that, I'm wrapping up. As I said, this was meant to be a very quick 30-minute overview of some high-level comments or concepts. So if there's any questions or comments, I could take them now or field them later. And there's my contact information if anyone has any desire for more detailed information.
Thanks, Kevin. We have one question in, so we could just take care of that right now before we get to Emma's presentation. What determines nodes or subsections of a feeder? And I'll add, why is that even relevant?
So when you talk about nodes and sections, this is, the distribution circuit isn't just one very long line. There's branches that comes off, there's transformers connected. And so traditionally, a node is considered any point where there's a connection or a change in conductor. So if you've got a transformer that ties off, that becomes a node. If you T the distribution circuit and it goes different directions, that's a node. And so this becomes important because the more nodes you have in the system, that means that when you mathematically model it, it increases the complexity. For distribution circuits, it's common that they will have several thousand, if not tens of thousands of nodes per distribution circuit. And so when you're looking at this in a mathematical term, that becomes a very large model to work with. And then as you start to add in all of these other devices, regulators, capacitors, generators, EVs, these all become elements you have to analyze. And so it's a good conceptual way to look at the size and complexity of a system. Does that answer the question?
Great, thanks, Kevin. Yeah, that's great, thank you. So let's go to Emma.
Hi there, can you hear me okay?
Yes.
The second piece of this presentation, and so normally when this was in person, me and Kevin would have a single presentation that we kind of talk back and forward on, but the way this is working out, it's easier when it's split out. The second part of this presentation was me talking a little more about the operations side of this. It's less about the detailed, how does all this work in operations, more about what all the different words mean that will actually probably be talked about in much more detail over the next 3 days. So do I have control? Sorry.
No, Emma, just please say next slide when you're ready.
Okay, cool, thanks. So there's 3 different pieces in here. Some of it Kevin has actually covered already, so I can step through pretty quickly. But the overview here is talking about what things like distribution, supervisory control, and data acquisition actually means, smart meters and advanced metering infrastructure, and various other pieces where we start to get into all the different types of MS or management systems that are involved in this. So starting off initially with just a few definitions here, we had EMS, which is Energy Management System, OMS, Outage Management Systems, and DMS, which are Distribution Management Systems. And by the end of this presentation, I will be absolutely sick of saying MS, but we'll get through it. So briefly covering—
Emma, excuse me, Emma, is it possible to put yourself on webcam?
Sure, I'm in an odd space, but I'll try, hold on. I don't know if that worked, but that was the best I could do at the moment. Sorry, my computer isn't giving access to different things just now, so that's me giving it a shot. So briefly covering here where the management of distribution and transmission actually is and where it's going. Later on today, and I'll try and get my webcam working for then if you like, is where I'm actually going to cover in detail what the different sensing and measurement devices actually are at the distribution level. This is more about where the data comes from in that regard. But here we're talking about where transmission and distribution SCADA is working. So next slide. So starting off initially, the SCADA platform also is generally, I think Kevin already introduced, at the heart of electric utility operations. It's where we primarily get real-time telemetry for different systems that support utility control sensors. It's much more prevalent in transmission. You'll hear a lot more about high voltage SCADA type systems than you do about low voltage. But as we develop more applications for management of the system, as Kevin was talking about voltage management, distribution SCADA is becoming pretty important. But as we move on a little bit, and I'll talk about that again later, so I'm trying to skip through a couple of things at the moment. But an outage management system is a tool that essentially utilities deploy to manage their grids and restore power during outages. It's evolved essentially from what was initially, and if you could go back a slide, sorry. What was initially a trouble ticket program to essentially this sophisticated computer system where you can visualize what's going on in the system. So prior to the introduction of computerized systems in history, calls would generally be received by the utility and may have actually been written up by hand or entered into a computer and printed out for someone to go deal with it. The tickets could be manually sorted essentially and given to the customer and responded to by the outage management team and then placed somewhere for further actions. Analyzers would look at the tickets and then determine where the outage was and then go and sort it out. It worked well back then. It doesn't necessarily work well anymore with all the different types of applications, with distributed resources in the mix, and also we just have better technology now to manage things. The early versions of when we moved into computer-based OMS were essentially used to improve outage prediction accuracy, to find the locations better and actually restore the system better. Initially, they were using a feeder tree, which is generally a static description of how they thought the system was connected down from the substation node out to the feeder, the transformers, and out to the customer nodes. It was the connectivity-based system used a database to represent those electrical parts or electrical relationships of the distribution system, and then essentially produced a table where it would tell you where the outage location was and where somebody needed to go fix it. Moving on from that to where we are now, there's essentially a new breed which you'll hear a lot more about later on, of outage management systems, which evolved over the past 10 years or so. I think Kevin's probably worked on some of them as well. But the systems are generally characterized by a GUI or a graphical user interface, which means that an operator can see one or more things happening at the same time, or even just look at the entire distribution system when they're visualizing, say, a very large outage that's affecting many customers. There's a few different origins for where the data comes from on that. There is distribution planning models, but both of them are based generally in the geographical information system, where they essentially import a version of the topology and geography of the distribution system. So when they're sending someone out to fix an outage or investigate a problem, they know where they're going and they know the topology of it and they know what it looks like. It also helps them basically locate these things a lot quicker. And there is more connection now to measured data systems, including distribution SCADA also. So next slide. The next sort of stage that people talk about is the distribution management system functionality, which is not necessarily the outage management system, which is generally where you're looking for the trouble parts of the system. DMS is where you're actually trying to manage the system in its operational state where it's working well. It's how we put in new different types of applications. It can improve the outage management system in that it can implement various tools that will probably reduce the number of outages that you have and help locate things faster. But it's not the outage management system. So pulling them together, there's different functions here. So outage management is where people track and restore what's going on with the outages in the system, whereas DMS helps to optimize the operations over time. So we can analyze things like the state of the system, all the Volt-VAR applications that you heard about already, how the load is flowing. So if you're looking for overloads that could be managed by new applications or by something like demand response, then that can be managed under the distribution system, management system. And then Flizzr is a fault location tool also that I'll mention a little bit later. So different systems, but yeah, you hear them interchangeably quite frequently by accident because not everyone necessarily knows entirely which application is meant to go where, and also it changes over time. So in some different utilities, they might actually be using a DMS and an OMS or various functions of it together. And they're all for management of the system, but there's various different ways it's used interchangeably. So next slide. So another evolution of all this, and I know there is probably a whole presentation on this, is the ADMS system, which is the Advanced Distribution Management System, which does actually try and bring together features of outage management, optimization, and distribution operation together. So there are about many utilities and distribution organizations are evaluating the tools they've been using here and trying to integrate those three key systems together, including the SCADA and sensing and measurement system, the advanced metering infrastructure, which is where your smart meters come in together, and the DMS into one system called the ADMS. It's an integrated solution essentially to eliminate some of the sort of redundant processes, as I just mentioned, help maintaining a singular network model so that people don't have different sets of information in different offices. It also improves efficiencies in how people communicate and manage different parts of the system. If we integrate SCADA and different measurement systems to this, it also helps get to those more advanced applications for things like voltage management and some of the new distributed resource management systems that you might be hearing about as well. It's integrated, like I said, they're trying to integrate in various ways with the AMI type networks, substation automation, but this isn't just generally the sort of normal state for most distribution utilities at the moment. It's a good direction that things are going, but there's obviously various technology roadblocks that they're working through at the moment for how computation and cost and things like that as well. So next, sorry. So some of the different applications that you might hear about in there include like a lot of the automation work. Imagine when you're developing systems that can essentially manage themselves. They have different controls for voltage management, but those operators still need to see what's going on in the system, and this is the sort of place that sits. Also being able to predict the states of the network based on things like unbalanced power flow and presence of lots of different distributed resource systems in place, different load profiles, and also how do you integrate forecasts for the systems, not just for load, but how do you integrate forecasts for things like the distributed resources operation over the day, which will now impact how your distribution system is managed and how the voltage responds also. So just the entire goal with ADMS is essentially to improve operations by integrating a lot of disparate pieces together. But obviously that's a large task to pull together, and there's various, like I said, various roadblocks for getting it done, but there's a lot of work in that area at the moment. Next slide. We can actually skip through most of this at the moment because I think Kevin already covered a degree of it, but I had a slightly different set of slides if you want to read through them later. Obviously, I think they're all available. Essentially here I was talking about the different voltage management approaches and how that matches into where the ADMS, OMS, and DMS systems are operating. But skipping through these just now, I think we're okay with what's already been said. But I did give a couple examples here of what the different voltage profiles along a distribution feeder might look like based on different types of operation. So referring back to that standard that Kevin mentioned for what the service voltage ranges are, normally, as he said, from the source, that voltage will decrease over the length of the feeder from where the customers are. But if you look to the next slide, you see how the distribution management system for voltage might be operating, where they have, say, line regulators in place, which will help bump the voltage in the middle of the line. Or there might be a capacitor sitting at the end of the line to boost the voltage over there as well. So just showing what a voltage profile actually looks like to give a little bit of a visualization of what you're seeing throughout the 3 days as well. So next set of slides. Sorry. Okay. So the last piece I'd put in here, and I'll go through this fairly quickly as well, because I think we want a few minutes at the end for questions. I'm switching roles a little bit again. I'd mentioned advanced metering infrastructure applications and smart metering. I do have another section in the cyber and communication section where I talk a little bit more detail about what different types of sensors are. But I think when the realms of operations, we wanted to talk about where smart meters and data analytics fits into that grand vision of how the distribution system will be operated in the future. So smart meters are essentially rolling out across a lot of networks. I think there's about 100 million was the last number I'd heard, and Joe can absolutely correct me if that's not true. They allow a large amount of sort of fine-grained electricity consumption data to be collected and analyzed for how the system is operating, but also for giving people, the customers, a view of what they are doing on a daily basis and how the small changes they might be making to their own energy efficiency for various reasons, how those actually impact their billing and daily profiles is one of the big uses of smart meters for customer interaction. But why is a smart meter different from other meters? On the next slide, smart meters, I have a joke at the moment, and I can't see people's faces, so I'm not sure if anyone will laugh. But in my office just now I have a collection of different meters over time, and I was asked to remove a bunch of communicating equipment from my office. One of the meters that was sitting there had a rotating dial on it and absolutely no way to talk to anyone. And I was asked to remove it because they thought it might be a smart meter. But it was not connected to anything, so that was a little special. So that's one of the actual sort of key features of smart meters, is that they can provide communications, and essentially bidirectional communications and control. They can be linked to other types of components and back to the utility for giving improved notifications. But one of the key functions is essentially improved communications and automated communications in there, along with sort of higher fidelity data, more accurate billing, being able to actually monitor. And some of the more advanced types of them, there's ways to monitor power quality, for example, being able to use resources a little better in that there's remote disconnect functions and reconnection. Improving reliability, and some of those applications are in the other slides. So being able to see where outages are in advance using the measurement system, and also for, so as I mentioned, this more accurate billing, along with load forecasting. If you know what's been happening in the past over a period of time at set temperatures and times of the year, then you can use that data to better forecast what's happening in future also. So there's a lot of different applications as these are rolling out, and I think there's large fields of research going into new ones every year. So there's, as the different technologies also improve, meaning that the things like onboard computation come into play, then there's a whole host of things that can be done there as well. So stepping on. So I think I'd taken some of these slides from Joe and his smart grid program work here, where there was a number of projects where the meters were used to the best of their abilities to actually perform these advanced functions. So things like being able to look at service disconnections or reconnections after an outage, where there was a high degree of operations and maintenance savings, because we can actually reduce truck rolls by doing that, meaning the utility doesn't need to send out a person to physically do an action because the meter was able to do it from being connected to the outage management system and the DMS and the distribution management system. So there's a various metrics that are used here to do with truck rolls, to do with cost per truck roll. But I think this example here from one of the co-ops was used to show that they'd avoided 6,000 truck rolls by deploying smart meters everywhere. There's also various other applications they can find, which might include meter tampering, meaning somebody trying to bypass the meters so that they can get free power, essentially. Being able to detect outage, like I said, being able to see the clusters and where the outage is, and also improve the management of voltages along the system. The first part of managing your voltage is knowing what your voltage is. So being able to manage that is a key function. We can move forward fairly quickly on the next few slides. One of the ones I do like, the Florida Power and Light example. One of the things, and I was working in the last week and managed to damage a transformer, and this was actually pretty interesting. But the transformers with minor coil damage were something that they were particularly worried about in this area, but they weren't sure how to find distribution transformers. As you saw from Kevin's presentation, there's not just one on a distribution line that they're looking for. There may be however many hundreds sitting there, that it's pretty hard to monitor every single distribution transformer, even if sensors cost $1 each. There's issues with how all that data would even flow into one place. So in this experiment, or in this pilot, they were essentially looking to how to proactively manage the transformer program in distribution operations by using the smart meter data, and how do they monitor those voltages and determine if there's a particular problem. So this was a particularly successful application where issues were identified with a particular make and model of transformer that was out there, because there was consistently high voltages being read at those locations. With some fancy analytics being put on top of that, you can perform some pretty advanced features. So next slide. So this was one of the way this came out. Also, the visualization here is a pretty solid example of this as well, of how do you see where the voltages are, what are you looking at, and how do you interpret that. But as I mentioned, the analytics are pretty important. You need to be able to understand what you're looking at as well. And so in this example, that we're just looking at the voltages over time and working out where those faults might actually be. So next slide. Another, you can move on another one, sorry. And another one. Another interesting feature, I think I mentioned visualization a few times, is being able to actually allow a field crew to be able to actually see what's going on, not just with a piece of paper that's given to them where they go to a location, but being able to visualize the system themselves with a heads-up display. So more frequently now, you'll start to see your operations crew standing out there with iPads rather than with a notepad. And they may be looking at where the outage is, what the piece of equipment is, any sort of augmented reality type information they might have of what that piece of equipment, what the history of it was it replaced, is that the piece they're looking for. So there's, by improving the availability of the data into the OMS and DMS systems, they can then put that into the hands of the operators to be able to use the AMI system to a much higher degree. And the users can also then customize that to essentially see what they want to see and what they're used to seeing, for them to be able to look and work out what's going on. I think there's a lot of applications of this in the future, where putting smarter devices as well into the hands of field crew is a very useful activity. So next. So I think I'm getting towards the end of this, but one of the interesting applications which combines a lot of different things together has been FLISR, which is fault location, isolation, and service restoration. All those pieces kind of coming together into being able to restore the circuit automatically, and so get power back to the customers, or even just avoid a longer term outage. Basically, and if you look at the distribution system with these sets of houses fed from a couple of different substations, imagine there's a fault in between a couple of different houses, but they're currently all fed from one end versus the other. If they can use the AMI and other sensing technologies to be able to determine where that fault is, automated switching switching and self-healing systems can help you to then open the tie downstream, close the other tie, back feed to the houses. And then probably the only people that are actually impacted by it are the ones absolutely closest to it, rather than what you might be used to seeing when a whole distribution feeder is out for a number of hours because they're trying to restore the feeder from the substation as was, rather than reorganizing around the different switching patterns they have. So it's an interesting application where it brings together, like I said, AMI, OMS, and all the various systems as well. So last slide, I think. We can skip past that, it's a video. But. So I actually put a lot of the further reading that was requested in line in the slides. Obviously, I'm referring to a lot of different contacts here and different websites for people to look at, and I put them in line with the slides because sometimes it's easier for me to find things directly when I'm looking at the slide that I wanted more information on. So absolutely same as Kevin, feel free to contact me with further questions as well. But you'll also be hearing more from me later, so I'll talk to you then. But I think we have, is it 7 minutes?
Yeah, we have time. We have time for questions. We've gotten some good ones in the chat box. Thanks, both Emma and Kevin. So I'll start here with a question about voltage management. So the request is, can you talk about voltage management with inverters and utility equipment and issues to consider? It's kind of a big question.
Emma, you want me to take that one?
Yep, go ahead.
Okay, so using inverters to control voltage, it's one of these issues that is technically feasible, but the question becomes, how do you actively engage the customer's inverter? The reason I say engage is because it's not their job to do it. They're not compensated for it. And so the utility is held liable for proper operation of it. So if they rely on the customers to perform some level of service and they don't, it's still the utility's fault. So that's why I said it is technically possible, but getting the regulatory environment set up right to figure out how they interact with one another, that's really the biggest hurdle. And I made the comment about, what can happen with the inverters causing problems with traditional voltage equipment. That what can happen there is if you have large penetrations of solar and you have things like cloud transients, they can go from producing a lot of power to almost no power and then back up to a high level of power rather quickly. And that can cause the voltage to change very rapidly. That can in turn cause the voltage regulation equipment like regulators to tap a lot. And so they have to chase around all those transients. And so that becomes an impact on their lifetime. And then additionally, if they start to push enough power the other direction, that can change or could cause the change of power flow in the device. And you can have devices that are designed to operate with power flow going both directions, but many utilities, if they hadn't planned for that contingency, didn't buy equipment that was set up to do that. Once again, if they hadn't planned on it occurring, why would they spend the extra money for it? Because that would just be passed on to the ratepayers. And so you can have misoperation in some of those situations. So while there are some technical issues out there, I would say that the biggest hurdle is really the regulatory environment of what's the best way to try to rely on these non-firm resources, because they may or may not be there. Emma, anything you want to add to that?
Nope, all good.
And I think we'll hear a little bit more about smart inverters and voltage management in our next presentation from Patrick Dalton, so stay tuned for that. Here's another question, Emma and Kevin. Is the generation and production data, from a utility smart meter for a customer that has, say, solar on their rooftop, is that data consistent in measurements with, the question is about the customer's inverter measurements? So are the measurements from the utility smart meter the same as the utility might be able to get from the customer's distributed generation with an inverter? And if not, why not? And what are the considerations of using each of these data sources for, everything from load forecasting to modeling the system to planning the system?
Emma, want me to try that one? Take a first cut of that as well?
I'll add one thing quickly on that, and then you can take
Okay.
over.
Okay.
The way inverters are connected makes that relatively difficult to get the same level of data from AMI. Also, there's not necessarily a direct connection from your inverter to the utility. There's also various functions that are built into those systems that make that less optimal to use, in that there's safety functions where you could be tripping that system to do work on your house, for example, and then there is no data flow to the utility of what's going on with your system if you were using an inverter versus a smart meter. But Kevin?
Yeah, what I would say is they fundamentally are different devices. The meter that the customer has at their house, it's a revenue device. It's designed to track power. It measures on 5 or 15-minute intervals, and it's designed for billing purposes. And the utility has to have one of those for every single customer. So as a result, there's a lot of data there, and they can't be streaming it once a second. There's just too much there. Inverters, as Emma said, they are not even connected to that system. Many times they will just go to maybe the customer's home portal, or it may go to a third-party aggregators. There's fewer devices. There's a lot of diagnostic information. They probably have higher speed measurements. And so they don't line up because one's using 5 or 15 minutes, the other one might be streaming. But the key thing that Emma pointed out was these are on different systems. The utility doesn't have any legal access to the inverter data. That is a customer asset. Just as the third-party aggregator that is running that inverter has no legal access to the customer's meter data, and they would not be given access to the utility systems. So this is where we have this issue of data existing in different silos. And as was mentioned earlier, some of the concepts of advanced distribution management systems are looking at how you can kind of break those down, but they're not trivial. Once again, it's an example of, if you're just looking for a purely technical solution, most any outfit could probably have something done within a day to get them talking to one another, but they would violate all sorts of personal privacy laws, regulatory structures. So those are what need to be improved so that vendors and the utilities know how can we transfer the information and what our options might be.
All right, thanks, Kevin and Emma. So final question before we get to the next presentation. Looking at all the graphs where you're showing the voltage dropping over distance, what happens when there are distributed energy resources? Do the inverters on, say, the solar electric systems, do they match the voltage at the location? Do they provide any boosting capability to reboost the voltage of the power they output at that location?
So for the most part, customer-owned distributed resources do not actively regulate voltage. However, when they inject active power into the system, that tends to raise the voltage up. And so a challenge that you can have is, I showed the voltage dropping as you went from the substation. If you get enough inverters on the system, you can actually have what's called a voltage rise, where the end of the circuit can actually be much higher than the beginning of the circuit. And so that's a very difficult situation for the utility because the system was designed to operate one way, and now because of the way the customers are behaving, or I should say because of the actions of the customers, the system's behaving a much different way. And the customers have no obligation to minimize their negative impact to the system. They can do whatever they want, and the utility has to accommodate. And so those are the types of things that the utility has to consider and figure out how to operate with. It can be done, but it can be challenging.
So how would a distribution energy management system help with that?
Emma, you want to take that one?
Hi, sorry, I'm having mute problems, or just maybe problems with Tuesday. Sorry, if you're meaning a DERMS, that was one thing we didn't actually really cover.
Yeah, I'm talking about DERMS. Yeah, distributed energy management system.
Well, so they are designed to take in data from. There's cases where they're essentially managing multiple large distributed resource sites, or they're trying to manage clusters of distributed resources on people's houses. It depends is the answer to pretty much everything. There's so many different structures of how they would help, or how they would help manage those, that it's relatively hard to answer it as one type of thing. But if you take the systems where an aggregator or someone is managing clusters of resources that they know are in a particular service zone, then they could all be used to perform an action. I think that's one of the more recent functions that they've been doing in a few different utility areas, is allowing clusters of the resources to behave together to meet a global objective rather than a local objective. So the DERMS layouts are mostly used now for clusters for either financial or system-wide benefit. The smaller DERMS, which are where they're looking at the distribution level voltage, for example, voltage is a feature that you would like to be managed locally. You don't necessarily want to have to send out a control for everyone to manage their voltage. There's a lot of competing objectives that could happen there for the distribution feeders. So local control for those are generally, at the moment, optimal in comparison to using a large scale DERMS. But as things improve with measurement and analytics, then there's definitely applications where they could be used to help coordinate those resources also.
Thanks so much. I appreciate your responses to all these questions. I think people would love to talk to you for a lot longer, but we need to move on to our next presentation. Kerry, do you want to lead us off?
Oh, here we go. So next up, we have two of our presenters. Can I just get a sound check from Mr. Dalton, Mr. Langner?
Hello, can you hear me?
Great. Great.
Yeah,
okay.
hi, this is Rois Langner.
Hi, thank you. So next up we have Mr. Dalton and Ms. Langner for integration and management and control of distributed energy resources. Mr. Dalton, are you able to show your camera? Great, perfect.
Yes, thank you for the introduction and thank you for the opportunity to be here to present today. The questions that people were just raising are a great segue into some of the topics I'll be discussing here in terms of inverter functionality, managing voltage on the system, and a range of other topics. So next slide, please. Just starting with a few of the key takeaways in mind. The first is that DER integration considerations really vary by technology type and use case. So we'll look at a few of the main types of technologies and how that impacts the integration considerations. Secondly, there's really a standard set of physical and control impacts that grid modelers and planners look at. Sometimes the thresholds are a little bit different, but in terms of the fundamentals, it's pretty similar across the country. So we'll look at what some of those impacts are and how to mitigate them. And then also thinking about control systems, there are kind of autonomous, the inverter is controlling reactive power, trying to manage voltage on its own, and then there's centralized systems. And really, it looks like the future is some sort of combination of these decentralized and centralized controls when we think about integrating DER. And then finally, interoperability, or the ability to seamlessly exchange information for monitoring and control is really a key to integration in the future. So next slide, please. Actually, we can just advance to looking at the types of technologies. I've sort of boiled this down into two main types. We have rotating machines on one hand, and these are sometimes called synchronous generators, induction generators, and they physically have a rotating mechanism within them that is using electromechanics essentially to produce power. So it has a mechanically coupled response that's related to the speed of that rotation. By the nature of these devices, these rotating machines, they have a lot higher fault current. So if we think about protection, impacts, and a large amount of energy when a tree drops on the line or a squirrel or whatever causes a fault, that fault current is quite a bit higher than inverters. And these also have a very well-characterized fault current response that's based on the physics of the device. And they can sustain islands. They're actually a voltage source. They can create fundamental voltage on the system that can energize loads, and inverters can follow this fundamental voltage. However, rotating machines have very limited reactive power capabilities, especially for trying to lower the voltage or absorb reactive power. So there are limitations based on the stability of the devices. Inverters, on the other hand, are software defined. They're very highly configurable. The fault currents are quite a bit lower. So if we want to compare rotating machines to inverter machines, rotating machines can often have like 6 to 8 times the fault current, so quite a bit higher. And then inverters, since they're software-defined devices, the fault current response when there's a problem on the grid greatly varies by the particular manufacturer and how that device was designed. Grid interactive inverters aren't able to sustain an island or energize loads that are disconnected from the broader grid. They're really relying on that fundamental voltage from the grid in order to operate and supply current into the system. But they are, again, very flexible, so they have a wide range of these reactive power capabilities, which we'll talk about in the context of smart inverter or advanced inverter functions. So next slide, please. Zooming in a little bit further on the inverters, we won't go into the details of that block diagram in the upper right, but what I did want to convey with that is that these are largely software-defined control systems, again, and what they're doing kind of at the fundamental level is creating a voltage or a current waveform, by kind of quick pulses, and that's what's in the lower right hand of the screen. And so they can really, create this current waveform and either match it up directly to where the voltage is, and then there wouldn't be any reactive power in that case, or advance or delay the current in terms of voltage. And that's really, when we talk about reactive power, which we're going to get into a little bit further, that's really all it's doing. So the software defined controls of these current devices allow for very flexible operation over a wide range of conditions that contribute to kind of the voltage control that was just being discussed as well. Next slide, please. Rotating machines are still being deployed out there a lot of times for backup power, so they're not paralleled or connected to the system as frequently as inverters are. But since they're still part of the system, figured we'd spend just a minute looking at how they operate. So as I mentioned, these are rotating devices that have basically magnets in them and windings. And if you take a winding and you pass it over a magnet, you induce an electrical current. That's really the fundamental mechanism for these devices generating power. But they have a lot of physical limitations that we were just discussing in terms of managing grid voltage because of the rotating nature and the electromechanical nature of these devices. They are used in terms of like DER sometimes in hydro units, and induction machines are sometimes used in wind units, but even those types of DER are starting to transition over to inverter-based interfaces more and more often. So on the next slide, please. I'm going to very briefly talk about energy storage, and there are going to be kind of full presentations on this topic later, so keeping this part brief. But what I did want to flag about energy storage is that it's introducing additional control systems on top of the inverter control system. So it's basically adding another layer that increases the flexibility of the devices, and also need to manage, thermal constraints and estimate what the capabilities of the device are. And also wanted to point out that there's a draft IEEE standard P1547.9 that is providing guidance, or will provide guidance when it's complete, on energy storage interconnections and the specifics of energy storage compared to all other DER. So that may be available sometime mid to late next year. Next slide, please. Then in terms of, and this is probably intuitive to a lot of the folks on the line here, but solar PV is really driving inverter-based generation growth in the United States, and specifically looking at DER, which is the data represented on this slide. Solar DER is the largest capacity sector of all the DER, and all solar is going to be inverter-based. The other technologies could use an inverter interface, or they could rely on sort of more traditional rotating machine technology. So the point here really is that inverters are a growing and important part of the system, and thinking about how to integrate them is going to continue to be an important aspect here. Next slide, please.
Hi, Mr. Dalton. Before you move on, we did have a question. When you say that inverters are not able to sustain islands, does that include intentional islands with hybrid DERs, solar and storage?
It's a great question. So when I say inverters can't sustain island, it's caveating that they're grid interactive inverters that are certified to a specific certification, UL 1741, that tests specifically that they are not able to sustain an island, that they can detect and disconnect from the system. There are other inverter designs that are intended for island operation, and that could even be within that same inverter device, that when it switches over to an intentional island operation, that it's actually changing the mode within the inverter. But if it was in that intentional island mode, it's not in the mode that would be certified for grid interactive operation. So yes, there are certain designs that can, but largely when utilities are looking at interconnecting inverters, they're assuring that they're not able to sustain an island.
Thanks.
Yep. Good question. Yeah, next slide, please. So very briefly, when I think about a progression of integrating DER, in my mind, I break this down into at least a few different steps. Initially, there's really the physical connection and making sure that for how that device is connected in a normal operating mode, that there aren't going to be thermal protection or voltage types of issues. Interconnections, however, typically don't look at contingency configurations. So if there were switching, like we'll look at later in an example, that's not really accounted for. So a next step is to really think about how to integrate DER more broadly into planning and operational frameworks. So that could be contingency operations. That can be making sure that we understand what amount of load is hidden from a DER contributing to providing energy on the grid, and sort of larger system issues like ride through. Even further in the progression is really how to use the DER as an integrated resource for things like non-wires alternatives, avoiding traditional utility investments or market services like frequency regulation or other kind of advanced services. Next slide, please. Looking at sort of the fundamental operation of inverters, kind of that the interconnection piece of integration, what we're looking at here is a common voltage profile before there's DER. This was shown in the last presentation as well. Next slide, please. When we add DER onto the feeder, there can be reverse power flow, and that can elevate the voltage in the area where the DER is producing power. Next, please. There are really kind of two ways to reduce voltage from the DER perspective, setting aside other types of mitigations. Next slide, please. The first is for the DER to consume active power. So now we sort of have this opposing effect where the DER is injecting active power and consuming reactive power. And there's a cancellation effect in terms of the voltage rise that can occur, and how effective that is really depends on the system characteristics in the area. Then next slide, please. The second way is less preferable, and that's to reduce the active power or the watts, the part of power that a customer, a DER owner is compensated for. So this is generally reserved as like a backup option, and we'll talk a little bit later about how these reactive and active power functions can be stacked so that there's a primary response related to reactive power, which doesn't affect the output of the device if it's designed properly. And then as a backup option, sort of curtailing the power in real time. Next slide, please. And then thinking about sort of the planning and operational needs that arise, situational awareness, at least on the operational side, is a big one. And what we're looking at on the screen here is an example of two substations that are connected together through normally open switches. Those are the open white boxes. And as we can see, there's DER on feeders from the blue substation and one from the red substation. But if there were a need to de-energize that blue substation for maintenance, or there's some sort of issue, a transformer fails. Next slide, please. The system could be reconfigured. So whereas that large PV unit that was close to the blue substation may not have had an effect on voltage just due to where it was located, now that reverse power is going on a different feeder, and it could be quite a distance from the substation based on how it's reconfigured. And I mentioned that studies don't always account for these contingencies because there can be so many for even just a set of two different substations that it can be, with current tools and methods, not always practical to study all the configurations. So that really leads to a need to be able to monitor the voltage and the power output, the current output at these different locations, to be able to have that awareness of if you've needed to reconfigure the system, if there's potentially a voltage or a thermal issue created by DER, which we want to try to keep online even in abnormal configurations to the extent possible. But the tools are still really evolving to be able to do this well. ADMS is one of the largest solutions out there. Next slide, please. And what ADMS can facilitate is the monitoring, the direct monitoring of meter devices or the DER itself, but it can also perform estimation for DER that's not monitored. So thinking of all the rooftop units that might be numerous and not very practical to monitor every single one of those, at least today. Having some idea, an estimated quantity of how those are impacting the system is another important feature of a system like ADMS and can facilitate this type of situational awareness. Next slide, please.
And I think before we get into your next session, we will poll the audience. You had a really good poll for you to be a little bit more informed of what the audience is like. So I will, we're pulling up that poll right now. It reads, to what extent has your state started planning for and integrating advanced DER controls? The options are if you adopted smart inverters based on California or Hawaii state standards. Option B, modifying DER technical standards to prepare for equipment availability. Or C, we have active proceedings on the use of advanced DER control. And once we get a sufficient polling number, we will reveal the results. So I think, yep, the poll is closing and majority of folks said C. There are active proceedings underway. Thank you.
That's great. Thank you for that. All right, so moving into the standard control capabilities that will help facilitate DER integration, and by standard, I mean that these are based off of the IEEE 1547 2018 revision that is going to result in equipment availability, most expect sometime around the beginning of 2022. There are 5 different functions that all rely on kind of those 2 basic mechanisms that we discussed a few slides earlier of either controlling active power or adjusting reactive power. So we're going to zoom into a couple of these, the Volt-VAR function and the Volt-Watt function, which are offering a lot of promise as standalone functions, but also as coupled functions. You can couple one from the blue category with the red category, but everything in the blue kind of voltage and reactive power control, those are mutually exclusive. So let's first dive into Volt-VAR on the next slide, please. What we're looking at on the screen is the characteristic curve of the Volt-VAR function. What we have on the vertical axis here is reactive power that's either being injected or consumed by the DER. And on the x-axis here, we have the voltage of the system. So for higher voltages, the DER is going to consume reactive power, pull it from the distribution system, and that has that sort of cancellation effect that we discussed by opposing the direction of the active power flow. Next slide, please. And looking at an example of how this would operate dynamically over time, we're going to show a brief animation here, but I'll orient us to what these different graphs are before we hit go on it. Starting in the upper left, this is showing simplified loading of a distribution circuit over time. And below that, we're seeing basically an inverse curve where the voltage is going to be higher at times of low loading, and the converse is also true. And then if we watch this Volt-VAR curve on the right-hand side, that red dot is basically the operating point over time. And just to illustrate that this is a dynamic function that is going to react to the voltage. And next slide, please. So as we see, the voltage is high and we were absorbing current briefly, voltage goes low and we're injecting reactive current. That's basically the operation of the Volt-VAR curve. It's going to sit there constantly monitoring the voltage and react with current over time. Next slide, please. We'll play it one more time so in case you didn't catch it. So it's responding with a 5-second open loop response time. So it's not extremely fast, but it will help manage voltage, at least locally. The next function is this Volt-Watt. And again, we're looking at the characteristic curve where for normal voltages, we have active power on the y-axis. The DER is just going to be operating at its full rated power. But if voltage exceeds some threshold, V1 in this case, the power starts to be adjusted downward to try to help manage that voltage locally. And let's, on the next slide, please. Going to look at an example of this. So On the right-hand side of the screen, we have kind of similar to a few slides earlier where there's two different substations. The green box in this case is a normal open. So we have DER being served from that red substation at the top. Voltage is great, everything's fine. Next slide, please. But then we have an issue with the red substation. It struck by lightning, let's say. Next slide, please. We have automation in this case, let's say. So the fault is isolated. Next slide, please. And our DER is re-energized now from that blue substation at the bottom. But now that it's so far away, the DER is so far away from the blue substation. Next slide, please. We have the potential for a high voltage. So let's just assume that the voltage goes up to 107% of the nominal voltage. What we would see with this volt-watt activated is an automatic adjustment of the power output from the DER to drop to a lower level to try to help contribute to mitigating voltage rise in this case. So this function could be very helpful for these abnormal configurations of the system that we haven't studied during interconnection analyses in order to provide some sort of backup soft shutdown function. Next slide, please. And then thinking about stacking these functions, the Volt-VAR function is best suited for sort of day in and day out operation of helping affect the voltage. It's unlikely to be able to really actively manage the voltage, but by controlling reactive power, it can contribute and affect that voltage locally and help reduce overvoltages and avoid potential mitigations that might otherwise be needed. On the other hand, volt-watt is really reserved for abnormal system voltages to act as that sort of soft shutdown. Next slide, please. So what we've been discussing so far is all related to sort of local system, and we're going to very briefly, looking at the time here, cover some of the bulk system perspective. And the bulk system has sometimes opposing operating objectives to the distribution system. So it's an important discussion point between distribution system operators and transmission, how to really configure these bulk system responses. Next slide, please. But just to give a flavor of what the responses are, there are standard operating regions defined that contribute to bulk system reliability by having the DER sort of pull in the same direction as the bulk system needs. So we won't go into these regions in detail, but this was a change in IEEE 1547 as well. And next slide, please. These bulk system functions offer a lot of configurability in terms of what the set points are. And MISO actually went through an exercise stakeholder process to develop guidance for where these undervoltage trip settings in this case should be modified to be placed. And this has been common in other ISOs and RTOs, as you can see in the bottom right-hand corner, a little key of other set points to modify these undervoltage. But it is interesting that the defaults aren't really being accepted for undervoltage, and there's these stakeholder discussions to really figure out where these should be placed. Next slide, please. Now, transitioning into sort of interoperability, monitoring, control, management. Next slide, please. What's in scope of IEEE 1547 and is going to be defined is really this interface between the DER and the system. Everything upstream is out of scope. The network, what's going on in the backend system, that's all out of scope. Next slide, please. And in terms of what's in scope at that interface, it's really defining the monitoring, control, information exchange requirements, information models, so everyone's sort of calling an apple, so to speak. And then also the protocol, what language are we speaking in, French or German or English when we're referring to that apple. Next slide, please. And briefly, these are the standard monitoring and control and information exchange capabilities that all DER will have. So there's sort of the nameplate information, what am I, the configuration, changing all of the settings that we talked about for those advanced functions, monitoring, what's the real-time output, and then management is a different set of functions. Next slide, please. And how will this interoperability be used? It's really sort of monitoring that real-time operation, situational awareness. If you need to do remote settings changes, the initial settings don't work. The tie-in to ADMS and DERMS, which we'll very briefly look at. And then flexible interconnections as well, if we want to command a power level to DER based on the real-time conditions. That's another advanced use case. Next slide, please. Very briefly, just have a couple slides left looking at the time. In terms of accounting for DER and an ADMS, we talked about this briefly, that hidden load issue, but DER also poses other challenges for ADMS. For example, the FLISR module that the previous presenter was talking about, DER can interact with those modules, so it needs to be accounted for properly. Same is true for voltage regulation or integrated Volt-VAR optimization. There really needs to be close coordination. Next slide, please. And then in terms of like, where do ADMS and DERMS systems fit in? Here's one view of how DERMS, ADMS could interact with aggregators or even directly with DER devices. And there's going to need to be a growing focus on cybersecurity as all of these devices are networked and connected. And then some of the advanced functions, just thinking back to that three-step process of integration, the advanced functions are likely to rely on these types of systems to perform market services, non-wires types of solutions. So there's an expectation these systems are going to be increasingly important as time moves on. And that's my last slide. So same key takeaways as earlier, and conscious of the time, I'll hand it over. Thank you.
Thanks, Mr. Dalton. And we have a second presenter for this section. There's more resources here for your information on the slides on LBNL. And Ms. Langner, please take it away.
Great, thanks, Kerry, and hi, everyone. I'm Rois Langner, and I'll be talking to you today about how buildings can be a grid resource. Next slide here. So I am, sorry, one before that, I think I had an intro slide.
Rose, we move those to the back. Consistent.
Oh, okay. No worries. I'll give a little background to myself first before I move forward then. I'm a senior engineer in the Commercial Buildings Research Group at NREL. I'm an architectural engineer and a building scientist, so I am coming at you from a different perspective here, and really thinking about this integration, management, and control of distributed energy resources. I want to talk today about how buildings themselves can be this resource to the grid, and how we're thinking about that from the National Lab level, from the Department of Energy level, on how buildings can be more flexible and how they use energy to really provide that resource to the grid. Next slide. A few objectives for today's call. So we'll be looking at what are the impacts of buildings on the grid today. How can buildings be flexible in how they use energy? And what are some more dynamic signals from the utilities that can be used to help better manage buildings' loads? Next slide. So in this next slide, thanks to Lawrence Livermore National Lab, I'm sure many of you are familiar with this, but I like to present this because this really shows our estimated energy consumption. This is from 2019, and on the left side of the slide, you can see the different fuel sources that enter our grid. out of the total energy, I like to think about 3 different buckets of uses here, and those are located in the pink boxes on the right side of the slide. So buildings, both residential and commercial, consume about 1/3 of our energy. Industrial processes, which does include buildings, consumes 1/3. And transportation, which often transports people and products to and from buildings, is about 1/3. So buildings consume a significant portion of our total energy use, and as far as our electrical generation, they actually consume about 75% of what we generate in the US. Next slide, please. This slide is just showing how buildings consume energy and how that's changed over the years. Since 1980, we've seen more than 35% increase in residential energy consumption and more than 72% in the commercial side as well. Of course, that's because we've had a lot more construction happening across the nation, but it's been a serious jump. And with that, we've had a lot of focus in the past on energy efficiency and how do we reduce building energy consumption. But now we have more and more variable renewable energy generation coming online. We've been having, as many of us have been following the news, extreme weather events and other natural disasters that are hitting more frequently. And there's just much more urgency for buildings to not just consume in our normal manner, but to coordinate our consumption with the grid needs. And they can. The next slide. And that's what I'm going to be talking about today. So a little shift in focus here, but how can buildings be interactive and efficient? And we've heard this term in the last presentation, but grid interactive efficient buildings. The acronym is GEBS. There's been a lot of opinions on that acronym. And I actually really like it because of this pairing of 2 keywords, and that's interactive and efficient. So I'm going to talk about what are GEBS, why are they important, and what are the benefits to both the grid and the building owner. Next slide. So when we talk about GEBS, GEBS are really about enabling buildings to provide flexibility in energy use and grid operations. 80% of grid peak demand is driven by buildings. A little more than 10% of grid infrastructure costs are spent to meet the peak demand that occurs less than 1% of the time, making those peak times the most expensive and likely carbon-intensive power. In addition, on the consumer side, on the building owner side, they can see demand charges that can be up to 60% of their energy costs. So it's now this growing importance that we must focus on building peak demands and how to manage that in a more in a better manner that works with our grid. Next slide. So some key characteristics of GEBS. As in the title, GEBS are efficient. So I'm not going to spend much time on that. That's just reduce our energy consumption. They are connected. And I'll pause here because this idea and concept of a smart grid has been around for years and years, actually. It's not a new concept, but I do believe that now we actually have the technology and the analytics to really push forward our buildings. We have equipment that are IoT enabled and connected. They offer 2-way communication between equipment and a building automation system or a home energy management system. We have advanced analytics that really enable the smart operations that are often supported by multiple sensors and controls that are more readily available on the market these days, and we can optimize our efficiency and the flexibility while maintaining occupant comfort in buildings. So all of this together and paired with some of these distributed energy resources like PV and battery systems, we can really operate our buildings in this more flexible manner, reduce our energy consumption, shed the load, shift it when we need it on an hourly basis throughout a day. Next slide. In this next slide, I'll just show a couple examples of what types of systems can be controlled in more flexible manners. And it's most of the systems in buildings. This is representative of a commercial building in this case. And I'll talk through this in more detail on some of my later slides. But HVAC systems, there's a lot of opportunity to ramp fans down, for instance, or stage operation of equipment so that they're like electric resistance heaters so that they're not operating all at the same time. Or setting different set points or pre-cooling, preheating a building to shift the load to off-peak times. We also have the capability to work with our lighting systems to turn lights off, reduce the lighting load, just dim the lights a little bit so it's not that noticeable to the occupants. We can rely on battery-powered equipment, plug-in battery-powered equipment, like laptop computers or even electric vehicle charging. Can we use those batteries to our advantage so that we could shed load during different times of the day or shift the charging to another period of time when it's more appropriate? Thermal mass is a huge component or attribute of the building that we should be taking more advantage of, whether through water heating systems or through the actual inherent thermal mass properties of the building itself, concrete floors or other mass just in a typical building. Can we use that to store heating and cooling so our systems don't need to run as hard during peak time? And with this, we're getting smarter equipment in our buildings. The equipment is better connected to our automation systems, our home energy management systems. So we have this two-way communication between specific equipment inside the building, but there's also this capability with other communication protocols such as OpenADR, where we can communicate with the building to the grid and receive signals from the grid on when to reduce the energy consumption of the actual building. Next slide. So there's 4 demand flexibility modes that we really highlight here. First one is energy efficiency. Of course, this is just reducing the load profile of a building. Load shed is what we're more interested in as we talk about GEBs and load shift and modulation. So load shed is just reducing our peak load for short periods of time throughout the day, so a couple hours perhaps. This can change on a weekly basis or depending on the day of the week, and it might have seasonal impacts as well. Load shifting, similar, it might, the time of day that we can shift load, and a great example of this is pre-cooling a building. So running the chillers in a building during off hours, maybe at night, to pre-cool it. So during the heat of the day, a building is not running their chillers quite as high. So that's just shifting the load to these off-peak hours. And then modulation is this very slight increase or decrease of the building's power at the sub-seconds level. And this really provides this grid resource for balancing load on the grid. As various loads come onto the grid and come off to the grid, buildings can respond and provide this slight modulation in their own electrical load to help offset that. Next slide. So when we combine these together, and again, these slides are representing our load profile of buildings. So efficiency, we're just dropping that load profile. When we include the generation side, renewable generation like PV, we are often stuck with what we're calling the duck curve, right? With these drastic drops in energy consumption and drastic rises in energy consumption that the grid needs to accommodate. So when we can be smarter with how buildings use energy and more flexible in that, we're really trying to even out that curve. So we're not seeing such drastic spikes and dips in the energy consumption in aggregate, and we can even that out to more predictable loads that the grid can accommodate, and especially as we have more and more variable renewable energy that's coming online. Next slide.
Sure, and I think you have polls after this slide.
After this slide, okay, great. So potential benefits, there's a number here. I'm just going to focus on a few of these, but really on the grid side, if we can be more flexible with our energy, it does provide us improved reliability and resiliency. of our electrical infrastructure. It reduces grid congestion. There's even environmental benefits if we can use energy during cleaner parts of the day, so we can actually reduce the greenhouse gas emissions, or use energy when those greenhouse gas emissions are lower. On the building owner side, I think it really comes down to this energy affordability side of things, where we can really focus on peak demand and continuous peak demand management and reduce those peak demand charges. So with that, I think we can go into the poll questions. I just have a couple here to gauge your engagement on this already. So does your state currently consider buildings as a grid resource? 3 responses: yes, you're exploring leveraging flexible buildings for peak load. Not sure, you're new to this topic, but excited to explore these opportunities. And no, flexible loads do not enhance business or operational needs. Great. So this is excellent. So it's great to see that even 6% of you are exploring leveraging buildings for peak loads. That's great to hear. I'm not surprised that 71% is not sure. This is a new topic, and that's helpful for me for how much detail to dive into here. And also interesting to see the 23% no response here. And I would be curious maybe in the discussion later to explore that a little bit more to see if you think that your business or operational needs will change down the road. And then do we have the other poll, or are we continuing on here? Okay, great. So the second poll question here is, what do you think the largest barrier is to implementing demand flexibility? I've included a number of responses here: engaging building owners, technology limitations, utility rate structures to incentivize peak load reductions, and integration of renewable generation and battery thermal storage. Great. Utility rate structures to incentivize peak load reductions has 57%. Building owner engagement is 26%. Integration of renewable generation, battery, thermal storage. Yes, I see that. And nobody chose technology limitations. And I think that goes back to my point as we're ready to move forward with this on the technology side. But there's a lot of other hurdles that we do need to address to actually make this happen. So thank you for those responses. Great, thank you. And then next slide. So I do want to point out, as I just mentioned, we are advanced on the technology, but I want to talk through some of these inherent building pieces of equipment and end uses that can be controlled in these more flexible manners. On the residential side, we all live in a home, so I think we have some personal connection here. But thinking through smart thermostats and how those can be leveraged to modify temperature set points and preheat, pre-cool during off-peak hours. There's smart appliances to shift operation. Electric lighting, of course, can be turned off or dimmed. Water heating and thermal storage can be leveraged to shift heating and cooling loads associated with heating and cooling the house, and then also water heating. And of course, electric vehicles and chargers, there's a lot of research happening now too in thinking through optimizing charging of electric vehicles and when the best times are, and how do we coordinate that with the grid depending on the building type and the operation. Of course, battery and solar PV contribute to the load flexibility as well. And next slide. On the commercial side, it's similar in that we can control our lighting to dim light shed capacity there using automatic window shade devices. On the HVAC side, there's a number of strategies that we use, of course, with temperature set points, leveraging thermal energy storage, and then staging of certain equipment like air handling unit fans or electric resistance heating so that they're not all running at the same time. And if you think of a building that does have electric resistant heaters, for example, you can maybe run 20 or a third of the electric resistance heaters for 20 minutes during an hour, and then shift to the next third, and then shift to the next third. And that drastically reduces that energy load of the building. Again, can we leverage equipment that has batteries to shift loads, shift the charging of those equipment to better times of the day? And how do we better integrate our solar PV and battery storage to really optimize performance for both the building and for the utility as well? Next slide. So in summary here, we really can leverage existing equipment in the building. Some of these technologies may or may not be smart. You can do manual controls, or you might have technologies that could communicate with an intelligent control platform or a building automation system. These technologies may offer one or two-way communication with the grid, and I think we're going to see more and more technologies like that on the market. Moving on, building managers can control these individual equipment, or they can leverage software solutions, which I'll talk about more in a moment, that can really optimize multiple end-use systems. And flexibility can be provided through response to specific demand response events that the utility is sharing with the building owner, or they can continually manage their demand on their own, which does provide more financial incentive to the building owner as far as reducing demand charges and overall energy use of their building. We've really operated and modeled buildings in a very static way until now, and now we really need to think about how do we think through more dynamic signals that can be leveraged to optimize the building energy consumption. So these dynamic signals, of course, include time of use utility rates if they're available, or near real-time carbon emission rates, or weather signals and occupancy signals within the building. So again, we're moving towards this. We have the capability to have the analytics to think through those dynamic signals more critically and control in a more optimized manner. Next slide. I want to share a little bit about how the national labs are thinking about how do we characterize these gas technologies and solutions. And this gets in the building science weeds, but I think it's important to see how we're thinking about this and how it could relate on the larger grid scale too. But the way we think about it, these technologies is what is the capacity of flexibility that these technologies offer with the functionality, what end uses are targeted here, what types of flexibility modes are supported. Important ones are the communication protocols that it uses to communicate within different devices in a building, and then also to a utility. More relevant, I think, to the utility side might be the response time that a building could have to a demand response event, and how that building can ramp down or ramp back up quickly to respond to those signals. And we're starting to really test this, and I'll talk about some field studies that we have underway right now moving forward. Patrick also mentioned cybersecurity. This is always a huge question in mind when we start implementing these connected smart technologies in our buildings. Next slide. So talking about software solutions, we are seeing more and more comprehensive software solutions that are coming onto the market. Kerry, I'm not sure if you heard me, but if you could advance the slide, that'd be great. These software solutions connect to building automation systems or home energy management systems. They are touting that they can control multiple building end-use systems. They may offer one or two-way communication with the grid. They're providing these advanced analytics and flexible control. They trend the data. They capture multiple signals, occupancy, weather, utility rates, trended load data, carbon emissions. They have the capability to do all of this. So I'm excited to see that, because that seems like a more comprehensive solution and easier solution for the facility manager, and a more enabling solution that can really connect these individual buildings to a community of buildings, and that community of buildings to the grid, so that in aggregate, these flexibility modes will have more impact to the grid. Next slide. So the end goal of all of this is that we are looking for more flexible and optimized performance. How can we be more responsive to the building and grid needs? And really, how are we reducing our peak demand and lowering demand charges? Next slide. And lastly, before I wrap up, I have a few slides on this, but I wanted to briefly talk about some field demonstration programs. Looks like my slide is, I don't know if that's coming through on your end, but there you go. The General Services Administration, Department of Energy jointly release a request for information every year. We actually just released a new RFI focused on resilient and efficient technologies. So if you haven't seen that, that is out there right now. If you go to GSA's Proving Ground website, you should see a link to that RFI. But last year's was focused on GEB solutions and more of these comprehensive software solutions that enable multiple flexibility modes and integrate multiple building systems that go beyond integration of just HVAC and lighting, and that can dynamically manage and coordinate the loads. Next slide. So from this RFI that was released, we selected 5 GEB solutions, so software solutions that we will be demonstrating in real buildings. 4 of the national laboratories will lead the measurement and verification, including NREL, Lawrence Berkeley National Lab, Pacific Northwest National Lab, and Oak Ridge. And we will be testing these in both federal GSA and non-federal buildings. Next slide. And because these are so complex, they're just highly complex solutions, we're really trying to understand what the capability is of these solutions to enable efficiency and load flexibility continuously and in response to DR events. What are the costs of these solutions? Does it meet the building owner needs? Does it provide utility benefits? And is it pretty easy to integrate? So we will be working with utilities on these projects as well, as much as possible, and with those utilities that are interested in participating in the project. And I'm just really excited for these field demonstrations. They're really the first field demonstrations in looking at load flexibility and how these software solutions can actually perform in real buildings. So stay tuned for that. And my very last point here is, what we've recognized in this new field of load flexibility is it's really important to coordinate our language and metrics and our approach to measuring and verifying load flexibility. And these are going to be, again, complex. They're different building types. They have different uses. They'll have different equipment. They'll be looking at different load flexibility modes. But we've come together, and we, as in the National Labs, GSA and DOE in particular, Lawrence Berkeley has developed a lot of metrics around how do we quantify demand flexibility, load flexibility. NREL, Lawrence Livermore, Pacific Northwest National Labs help too. And these are just some of these metrics that we'll be looking at a higher level so that we can better compare these solutions in field demonstrations and share what the potential is in those unique scenarios in meaningful ways. Great, and last slide here. I just want to point you to a few resources for more information. So DOE has what we call their GEB site. This is a repository of all of their published report series focused on GEB-related work that the national labs and other experts in the field have put together. So this is a great resource to see what Department of Energy has done in this GEB space. The second bullet there is the Better Buildings Alliance Renewables Integration Team. So I'm the technical lead for this, and historically, this has really focused on strategic integration of renewables into buildings, but we've really shifted to this load flexibility, demand flexibility focus for our team. So if you're interested in joining our team calls, please contact me about that or go to our website to learn more. And this last one is a recent publication from Lawrence Berkeley National Lab on performance assessments of GEBs. So those are the three. And with that, I'd like to thank you all for listening today, and I look forward to your questions.
Hi, thank you. We did have a question on cybersecurity, but I think we're going to punt that for the 3:45 session. Just a really quick question. So we have our full break. We have somebody who asks, what is the cost benefit consideration of GEBs versus just engaging primarily with energy users? And you touched on this a little bit, but if you could elaborate.
Yeah, and more so on the commercial side, commercial building owners experience just very high demand charges. So I think that the benefit there is if they can continually manage their peak demand, which actually many building owners are already doing this, then they can save dramatically on their utility costs. So there is a cost benefit to the building owner there. I think we need to think through a little bit more on the utility side and that engagement and what the incentives are from the utility to really drive the building owners to act. For example, residential consumers, if we don't have time of use utility rates, what is the incentive to drive a residential owner to operate their building in a more flexible manner? So I think we are moving towards these more dynamic rates that are coming out. We're seeing a lot or more examples of time of use utility rates out there. But I think that there needs to be more of a connection and an understanding of the value that buildings can provide to the grid itself to drive that conversation.
Great, thank you. And before we break, I just wanted to thank our panelists, Ms. Langner and Mr. Dalton, for your expertise today. And I also wanted to mention that if energy offices or utility commissions are interested in additional information on GEB, we have a working group on that. And then we also have a new project on cyber and solar. So stay tuned for more information on that. But for now, we will cut to the break and we will see you back at 3 p.m. Central Time. Thank you all.
Thanks so much.
Hello, Lisa. Can you hear me all right? I don't hear you.
Jeff, can you hear me?
Yes, Paul, I hear you.
Great.
I think Lisa's just dialing in. Just give her 1 second.
I'm here.
Oh, there you are.
Okay, there we go.
Are we ready to roll, Dominic?
We're good to go.
All right, great. Well, thanks for coming back from the break. We have Jeff Taft from Pacific Northwest National Lab and Paul DiMartini from Newport Consulting Group to talk about transmission and distribution operational coordination. Thanks.
All right, thank you and good afternoon. Let's go to the next slide, please. We're going to talk about this issue in the context of a discipline we use to understand interactions in the grid. It starts with this concept of system architecture, which is a discipline used widely in many industries for a variety of purposes. And we add to that some things that are specialized for the grid, network theory and control theory and so on, and focus it on the grid. And we call that grid architecture. But the purpose of all of this is to understand large-scale systems in a somewhat abstract way, but being able to understand its properties. So we think of the grid or any of these systems as a set of black box components. Means we don't worry about what's inside them. Structure, the way the boxes or components are related or connect to each other, and the externally visible characteristics that we get. You can see that there are a lot of different purposes there. One of the things that we do is use this to think about the coordination problem for transmission and distribution, and that's what we're going to focus on today. Next slide, please. So the coordination problem has become one of the largest problems in grid modernization, and it's because of the proliferation of assets that can participate in the operation of the grid but may not be owned or directly controlled by the utility, largely distributed energy resources. So operationally aligning all of that is what we really mean by coordination, and that is a significant problem because of the fact that you have multiple owners and multiple ways to control these things. So the 20th century grid did not evolve with that concept in mind, and consequently things have been developing organically to try to deal with this, and that has led to some issues with coordination, some structural problems that have evolved, and we're going to take a look at those on the next slide. So one of the things that can happen is hidden coupling, and it can occur in a number of different ways. We have a couple of examples here. If you have a device, let's say this is a rooftop solar inverter or a storage unit or any number of things behind the service transformer, and you have two different processes that are somehow trying to control it, such as, for example, two different processes trying to use prices to devices methods to get it to do something, they can end up fighting each other. They can be in conflict if there's not a coordination between them. And we've actually seen this happen with one process overriding the prices left by another process. In the middle, another way this happens is two different control mechanisms manipulating devices that are on the same service transformer secondary. And because they're connected together at that level, there can be a conflict with those as well. And we've seen some of that with utilities controlling some assets and DER operators controlling others. And then finally, the one that we're mostly concerned with on the right there, a transmission system operator. That would be something like an independent system operator, a regional transmission operator, or the equivalent in those areas where we don't have that structure, who's responsible on a large scale, but is now managing things that are connected at the distribution level, when the distribution operator is responsible for distribution operations and reliability. So that can cause a hidden coupling through the distribution grid itself, and it may not always be obvious that this is happening. And let's look at the next slide to see why. When you look at the skeleton of all of this, and that's the way we break this down, you can look at what happens with the lines of coordination, and we can identify those fairly easily. And you see some things happening here. On the left, you see this thing called tier bypassing. There's a line of coordination that goes from the system operator down to past the distribution company, down to assets at the distribution level. And in the middle, you see that double-ended red arrow there. That's a place where there's a gap in coordination. There's no coordination between the system operator and the distribution company. And those are both things that lead to those hidden coupling problems that we just talked about. Next slide. Of course, it can be harder to recognize in real situations. This is an industry structure model. We use these to understand on a regional basis how the various entities involved interact with each other. And these are multi-level diagrams. So there's quite a lot of detail here, which we won't go into today. But the thing is, this is the environment, this is the background that you're making these changes in when you're thinking about coordination. It's kind of like having a tapestry. If you tug on a thread someplace, it's going to bunch up somewhere else, and you like to know that before you start to do things. In other words, you like to know about potential unintended consequences, and that can be quite difficult because of the complexity of the systems that you see on a regional basis. Next slide. So we started to look at this problem in terms of how could we think about it on a rigorous basis, and I'm not going to make you do any math today. I will just tell you that we used a mathematical basis to derive a structural framework to think about coordination. And that structural framework has some nice properties. It gives us a building block that we can apply at all kinds of different levels in order to think about how to put together a coordination framework that can operate from top to bottom and whose properties we'll understand. The basis for this gives us the ability to solve problems in a variety of different ways. So we haven't picked a particular set of equations to solve or anything like that. We're more interested in the structure, but it allows for allocation type solutions, that is to say direct control type solutions, and it allows for price-like methods, in other words, market type solutions, and you can even intermix those in this arrangement. It's very scalable. And it can be built out on a proportional basis when you're implementing it. So it has a lot of good characteristics, and this is a much better approach than saying, well, let's just start drawing some lines and connect some boxes together and see if we can make things work. You'll notice that there is a building block in there. It's inside that red square in the lower diagram there. And if we look at the next slide, we can see how we can apply that. This is what we call a framework. That means we can develop any number of specific architectures that map onto any particular grid, and can do so at multiple levels. So we can apply this clear down at the individual device level, even inside a microgrid or building if we wanted to, or on the regional level. And that means that it helps us understand the issue of transmission distribution coordination and helps us understand a lot about how the roles and responsibilities might have to evolve going forward. You'll see a new term there, DSO, and we're going to talk about that a lot in this discussion, distribution system operator. Let's go to the next slide. The architecture development that we just talked about gives us some simple rules for how these things should be structured. So we remember this little coordination framework diagram on the left that we just looked at a minute ago. The framework gives us some simple rules to allow us to transform that into something that does not have the problems we identified, the tier bypassing and gapping. When you do that, you get a diagram like the one on the right. And that automatically starts to inform about what that new thing called distribution system operator ought to be. So it helps you understand what the roles and responsibilities are that go with that, and helps you understand about the interfaces between that and other parts of the system. Next slide, please. Because of that, you can understand now why you would say that the distribution system operator would have a role that involves how things transpire at the interface between transmission distribution, and allows the distribution system to look very different. It allows it to look like a virtual resource. So at that interface, you come to an agreement about the exchange of energy and services and so on. And that changes the nature of the relationship between distribution and transmission, but it gives you a powerful new way to think about how those two can be coordinated together, how that gap that we showed before gets filled in, what the nature of the roles and responsibilities are, and what the nature of the interfaces are, and what kinds of information should flow across them. Next slide, please. So people have given a great deal of thought to this, and Paul in particular has worked on this with Lorenzo, Christoph, and others to define some thinking about what is a distribution system operator. And there's a spectrum of models that they have thought about. On the left, sort of one bookend, is what they call a total transmission system operator. And there, the optimization and all of the dispatch and so on are very centralized at the transmission system operator level. The DSO still has some responsibilities, but they are mainly reliable operation of the distribution network and providing visibility of that to the TSO, and the customer or aggregator coordinates with the transmission system operator in that model. All the way over on the other side, the other bookend called total DSO model is very different in that the transmission system operator still optimizes the bulk system, but it sees distribution as a single virtual or aggregated resource managed by the distribution system operator. It doesn't have visibility deep into the distribution system. The distribution system operator is responsible for all that physical coordination and aggregation of services at that interface, and the customer or aggregator only deals with the DSO in that case. In between, there are a range of hybrid models, which are compromises between those two in essence. They're more complicated in the sense that they split up the roles and responsibilities in different ways and require that the customer or aggregator coordinate with both the TSO and DSO. But we see a lot of that thinking going on, not just in the US industry, but around the world. Next slide, please. So let's look at these a little bit more in diagram fashion. The total TSO model, the one that was all the way on the left, you can see everything flows back to the transmission system operator. All those lines are flowing uphill to the TSO, and you see how the aggregator deals with the TSO and how even the demand response programs deal with that. And the distribution operator, in a sense, is off to the side. There may be some amount of information exchange to help do coordination, but fundamentally, really, all of the real management of the whole system is at the TSO level. Next slide, please. So the hybrid model, this is the one that was in between on our spectrum, is more complicated. You can see now that you've got lines flowing to both the transmission system operator and the distribution operator, and you've also got a stronger line, more coordination between the TSO and the DSO here. But just by the nature of the way this is structured, you see there's more complication going on here. And in practice, where we've looked at this around the world, these hybrid models get a lot more complicated than even what we're showing here. Next slide, please. Then finally, the one that was all the way on the right on our spectrum, the total DSO model, you can see is very simply structured, and you see that clean interface between transmission and distribution. And you see that the distribution system operator is responsible for managing all the things that happen at the distribution level, including handling the aggregations. So that gives you a sense of the kinds of structures that people are thinking about. There are lots of variations on this, especially in the hybrid models, and a lot of thinking going on around the industry in the US and in other countries about exactly how to do this and how to get from where things are today to some version of this kind of coordination going forward. Next slide, please. So the process of doing that, both for the utilities and for the regulators, is not simple necessarily because of the complexity. Remember that industry structure diagram I showed and how complicated it is. That complexity can really be a problem if you don't have an organized approach to attacking this. So Paul had laid out a kind of an organized approach to it that you see here, with 4 basic steps that help either the utilities or the regulators or both think their way through this process of getting to a coordination framework. And the first one always starts with the thing that you always want to begin with is, what are your objectives? And then what capabilities will you need to meet those objectives? From there, you can think about documenting, and you should document what kind of structure you have now in your system, and if it is changing, if it's emerging, think about documenting that as well, because you need to know where you're starting from if you're going to make these changes. And then you can take a look at some alternative arrangements for coordination structures, maybe selected from within that spectrum that we talked about, and do evaluation on them finally in terms of both operational effectiveness and risks, and naturally always in terms of what it's going to take to do it and what the cost would be. So you can be very organized in a stepwise fashion on how to think your way through this process. Along the way, there are various things that you can draw from the grid architecture work to help you without having to be doing the architecture work yourself, but there are basic principles that help you at each stage of this. So let's talk a little bit about the evaluation process. Next slide, please. So there's some key things to think about in the both the operational effectiveness and risk area. On the top there, you see several things that are listed as effectiveness. So things that you want to think about are how much observability each of the entities needs. It depends on what type of model you're thinking about. How much does the DSO need to know, how much does the TSO need to know, and how much do they need to share. You want to think about that because that has a big impact on the information flows that are going to be necessary to perform coordination. You want to think about scalability. There are a lot of schemes around for how to integrate DER and do transmission distribution coordination that haven't thought out very well what happens when the quantities of DERs get large. A lot of things work well at small scale on the grid. In other words, you don't see the problems that are inherent in them. And then when they scale up, you start to see these operational problems. And you'd like to be able to know that the approach you're going to take is going to scale up nicely as the level of DER increases. Naturally, you want to think about the issues of whether you're creating or exacerbating cyber vulnerabilities, because we're always concerned about that. And some kinds of structures expose grid systems to more vulnerability than others do. And that's something that can be analyzed along with the rest of the work. And then thinking about the layer decomposition model, that's that framework we looked at a little while ago, helps you break this down into a set of subproblems that are manageable. So that building block approach that we talked about in putting together an architecture for doing coordination, this is a very helpful thing to do in terms of being effective. Some of the risks that we talked about, we already looked at. Tier bypassing and hidden coupling, we talked about those early on in the presentation. One more that we hadn't mentioned so far is what we call latency cascading. Some schemes for doing coordination require information to be passed through many different stages, many different organizations. And every time you do that, you create some time delay. That's what we mean by latency. If you start to stack those up because you have to go through many different organizations to get through one cycle of processing, that's what we mean by latency cascading. And too much of that is problematic because you start to develop instabilities in the overall operation of the system when that becomes large. So you try to minimize the amount of latency cascading that goes on, and that's a structural consideration and a risk that you would want to consider in doing all of this. Working with people who are familiar with architecture issues can help you sort all this out. It's not as difficult as it may sound. Once you figure out how to lay out and depict these things, it's actually pretty straightforward. Next slide, please. So some things to think about. A lot of the approaches to DER coordination now, to transmission distribution coordination, have some of the problems we talked about: tier bypassing, hidden coupling, cyber vulnerabilities. And a lot of that really comes about in the sort of hybrid approaches, especially if they are being developed on an ad hoc basis. The future models that we see people thinking about kind of have roughly two schools of thought. One is a centralized approach with the TSO sort of doing everything, and then layered approaches where the DSO has a significant role, which may vary a little bit depending on exactly how people want to do it. A lot of folks are looking at hybrid models as an intermediate step to get to one or the other of these, and those hybrid models can get kind of complicated, so you want to sort of be a little bit cautious about that. And then finally, we've laid out a simple model, the building block model that we call layered decomposition that I showed you, and the Occam process to help you think your way through how this is going to be structured. And that works at many different levels, including at the regional transmission distribution level. Next slide, please. So I think there are some poll questions that they have that are going to be queued up. Also, at the end of these slides, you'll see some items for further reading, a couple of documents authored by Paul and Lorenzo that give you a great deal more insight into transmission distribution coordination and the DSO models in particular. And then there's one from me that's pretty technical about the architectural aspects of all of this. We'll let you look at those as you want, and we'll stop there and see what kind of questions you all may have.
Dominic, do we have the poll questions queued up?
Yep, I'm getting them pulled up right now. Just 1 second.
So the question is, what is the main reason you would have for considering a DSO implementation? And we have 5 choices for you to pick from. Okay, this is pretty well split, but a third of you said providing distributed energy resource owners the opportunity to participate in electricity markets. And almost about the same amount said using distributed resources for non-wires alternatives, and the rest is split between regulatory compliance, resilience, and supplying grid services. And I think, you know, most folks probably would have picked more than one response to that, but the system we have, I think we just get to pick one. We have one more poll question, I think. Which distribution system operator model fits best? Your current view of the transmission distribution operational coordination, the total TSO model, hybrid, or the total DSO model? And then we'll get to questions right after this poll is over. We probably needed an I don't know response to that question. Although, interestingly, hybrid by far was the option that people picked, and I'm curious about that. Maybe I'll start there with a question. I think you said that the hybrid model is pretty complicated. You know, be careful. Maybe you can elaborate on some of the issues with respect to hybrid models again.
So I'll say a few words, and then Paul, if you want to add some into that, because we've looked at this actually in a number of different countries, and we've seen this sort of thing. And I think what happens here is people are somewhat reluctant to say we could go all the way to one of those bookend models. And so they start thinking about that and thinking about how could we compromise and get some of the benefits of that and still do some things similar to what we are now. That does lead to some complications, and some of those diagrams are, you know, the way people want to do it are kind of messy. So I'll stop there and let Paul chime in too.
Yeah, as Jeff said, they are the starting point for most discussions that we've seen around the world. And some of the work that we've done over the last 3 years have not just been in the US, as Jeff mentioned, but we did some international surveys for the Australian energy market operator a couple of years ago. And we looked at across Europe, we looked in Japan at their market restructure, obviously Australia and New Zealand, and several of the regions in the US that were starting to conversations. Everybody starts with a hybrid model and some variation of a hybrid. It's the compromise. And our view on it is that it's the logical place to start, but it's not going to be the ending place. And it's not clear we'll ever get to those two bookends that Jeff described, but it's likely that the trends will go towards one end or the other, depending on the structure of that market and what the needs are in that particular jurisdiction. But the thing that is really important is to the extent possible, try to keep things as simple and clear in terms of lines of roles and responsibilities, because if it's too complex, it really will start to create problems that will start to manifest pretty quickly here over the next 5 years in many markets that are having to have these conversations. So we named this Occam for a reason. This is named after Occam's razor about, you know, the best solutions are those that are the simple solutions. So don't let people get carried away with drawing lines on a board, just trying to connect dots and make sure everybody's communicating, because you start to create other issues. So clear lines of responsibility, clear lines of communication are really important.
Right, and just focusing for a moment just on the distribution system operator, that role could be filled by the utility, or as the paper by Paul and Lorenzo several years ago, 5 years ago, pointed out, can be a third party. Can you talk about sort of the pros and cons of the utility serving that function versus an independent third party?
I think in the paper we went through pretty systematically the pros and cons of having an independent distribution system operator and the utility provide that role. In retrospect, looking at where things have evolved over the last 5 years and continuing, particularly in those markets where you do have those states where there is a restructured market, I think that largely the utility can provide that role because they're really just in the wires business. The issue is there may need to be some equivalence of the FERC codes of conduct as it relates to transmission operations. We may need to have the same. There may need to be something akin to open access in terms of being able to have resources connect to the grid, but we largely have that in most states, particularly in restructured states, with wholesale access tariffs for resources to generating or battery producing resources being able to access markets and or retail tariffs that have exporting capability access. And so I think largely the open access is less of an issue than I think we had touched on in the paper these days. But I think perhaps the codes of conduct, but otherwise the cost in the studies that have been done today, both in the UK, most recently in Australia, and actually some work I just did as part of a team for the Ontario ISO in the province of Ontario. I think the cost of trying to stand up a separate entity to do the distribution side and then yet still have coordination on the physical reliability of the distribution system just adds another layer of interfaces that need to be maintained and managed so that you're not creating more problems, as Jeff was touching on. And the cost implication of that, I think, really bears out that I think with some rule changes or additional oversight, this can be addressed without having to create yet another entity that has to try and do something in the middle of all this, complexity.
Thanks. And is there some practical advice you can offer the state utility regulators here in this training and others to be able to work with the regional transmission operators, the independent system operators, to advance the planning of functions and operations that are needed at the transmission distribution interface?
Well, as Jeff said, it's this. It's really the second bullet. I think certainly getting the understanding your existing starting point, but as what you're trying to accomplish and understanding that what you're trying to accomplish in terms of objectives and capabilities will evolve over time. So having a clear understanding of what you need in the sort of the nearer term, say up to the next 5 years, but then having some view for beyond 5 years, out to 10 or so on or more, as it may relate to the resource planning or integrated system planning that may be going on in that particular jurisdiction. And then sort of looking at how you see the role of those resources that maybe today are largely behind the meter and not energy exporting, to over time where you may see increasingly larger amounts of those resources energy exporting, then that's going to change the dynamic in terms of the coordination that needs to happen from something that becomes much more active to be able to manage that, as opposed to something that's not as active in terms of managing energy exports onto the distribution. So I think having clear understanding of that and then being able to look at the roles and responsibilities and the functionality that's required is really important. Sometimes, as Jeff likes to say, people jump over and start talking about technology to manage all this, and that's not really the place to start. It really starts with what are you trying to accomplish and what do you need to be able to do to accomplish it.
In New York several years ago, going back to around about 2015, as you recall, there was all this activity called New York Rev. And there was a flurry of activity trying to figure out how to do this in New York to integrate distributed energy resources, and the New York ISO was involved and the utilities and so on. Maybe people may not know that within the last little more than a year and a half, the regulator and the joint utilities have sort of quietly revisited all of that. And what they have done is followed a process essentially like the Ockham process that you saw there. And they have adopted the framework that I showed you with repeatable building blocks as a framework to think about all of this. And so they've gone through those steps of actually documenting what their industry structure is now, defining the objectives they're trying to achieve, and defining the set of capabilities. And they've done it in a very thorough way. And they're working their way through to what is it going to look like for the market processes that they want to have to support the integration of DER. And they're very, very systematic about it. In the beginning, they weren't quite sure how those processes are going to work for them, but after a while, they really took to them and realized that those are pretty powerful tools to help them sort out the complexity. because complexity is sort of the big bear in the room with all this stuff. I showed that industry structure model diagram. That's really complicated. And to sort these things out, it helps to have some structure and some processes that help people get the insight to understand how to solve the problems. And we don't tell people, this is your answer, this is the way you do it. When we show them these methods, we say, here's how you can sort out what is going to be the best for you. And they've been applying that very successfully for some time now, kind of quietly, but one of these days they're going to release all that information and show what they accomplished.
All right, we have several questions that have come in from participants in the training. One is, how do you address the challenges of the distribution and the transmission jurisdictions competing for the operator role and the investments being made by each? And I would say certainly by the utility, but if it's an RTO, they're not actually making the investments. But if it's a transmission owner, that's the case there too. So the investments being made for modernization, and they're not necessarily coordinating it as needed for shared or clear delineation of what future responsibilities may be.
Yeah, it's a really good question, and one that a couple of states have started to explore it. In California, the use of distributed resources for non-wires alternative led to this, an aspect of this question, which is, so those resources that may also be participating in the Cal ISO's markets, how do you coordinate that activity between the two, and who has priority in terms of the use of these resources, and for what purpose? And where they ended up was using some clever techniques, one of which was that instead of having a separate contract, the power purchase type contract that would normally be used for a non-wires alternative, say services contract, the utilities are using a contract form like that they use for resource adequacy with generation resources. And in that, and this is also in coordination with the Cal ISO, the utility has right of first refusal on the use of that resource as they think they may need it in the day ahead. So on the day ahead, the utility determines whether they think they're going to need that resource the next day. And then if it's not going to be used, then that resource participates, it's scheduled into the Cal ISO on that day ahead basis. If there's a need in an emergency, say during the day of operation, the utility has the ability to basically override that dispatch and be able to do what it may need to do. It may need to have it shut down, not operate for whatever reason. And of course, there's going to be changes that happen as a result of maybe the distribution line goes out, the power's lost, and so therefore that resource can't, is out of the market from a physical standpoint. So these things, if we start to break them down in terms of looking at what the functions are, what they're providing the service, then it starts to become clear where the priorities are in terms of how you think about the dispatch and use of those resources. But as we think about this, what people call the stacked value, those values have different priorities. They have different time periods in which they may be used. And it's really taking and unbundling that, unpacking that, and really looking carefully and being able to understand who may appropriately have the first call on that resource to meet ultimately what we're talking about is the physical operation of the grid. And so whether that be transmission, distribution, or we're using the energy to optimize the economics on the system. So those have different priorities in terms of both how bulk power and from a state standpoint in terms of what customers see. So I think there's a way to work that out by systematically unpacking that and identifying priorities and linkages.
Thinking about one investment that's quite large that an RTO might make is in their visibility systems for distributed energy resources and any potential coordination with the utility, with the resource aggregators, and potentially even control. So if you're a state utility regulator and you see some competing investments between utilities and the RTO in that area, how do you grab your arms around it, before this kind of future has been defined?
Yeah, that's a good question. It was one of the questions that came up in the work that I was doing with the Ontario ISO Ontario. And one of the things there, you got one large ISO and you have about 50 plus local distribution companies in the province. And obviously it's and a lot of them are quite small. I mean, most of them are municipal utilities and they're quite small. So there, the issue was really that the distribution utilities weren't really, had necessarily the funds to be able to put a big complex system in. But on the other hand, they need to manage their distribution system. So how to bridge this relationship where there can be some sharing. So one of the concepts that I helped to develop and put forward was this idea of creating a common platform that both entities could access. So the information sharing that Jeff was showing in his diagrams could reside in a common platform, so both could have access to this. And the same sort of control functions could be available, but customized to what the respective needs are. So that is what the distribution company needs to do, say, to manage the non-wires alternative dimension and what the bulk power system may need for what it's doing, and being able to reconcile those controls so that you're not having that competing control issue that Jeff was showing in terms of the hidden coupling, but rather a platform that might be able to parse that and reconcile those. There are some technologies that are coming in commercially available that can help address this. I think we're still at early days, but I think there are some ways to think about doing that.
Are there any examples of sort of cost sharing in that regard for a platform like that could be shared?
Well, I think obviously in the province, since you're largely talking about governmental owned entities, whether crown corporations or municipal utilities involved, there's probably more of a government role in terms of the funding mechanism. But we have seen with probably most analogous are what we've seen with for example, in Texas with the Smart Meter Texas platform for data management, that it's a common repository that is used and was developed so that all entities could have access to the data that was in that repository. That ERCOT has access and actually, helps manage it from an administrative standpoint, but it could be some other entity. But and then the utilities and also the retail competitive companies have access to the data so they can, for their business functions. So we do have some models like that. They're complicated and can get quite expensive to develop, but we have some models where that's been done.
Also, FERC Order 2222 is recommending, not ordering, but recommending that system operators and utilities start to think about developing a transmission distribution coordination framework. They did not specify the nature of that framework. They're just sort of urging people at both of those levels to get together and start thinking about this, because that's what it's going to take because of the jurisdictional differences. So FERC is at least leaning in the direction of saying, why don't you all get together and work this out?
Yeah, it's certainly easier to do, like you said, Paul, in Ontario, where you have a big government role all the way around, and similar in ERCOT, you've got, it's the state of Texas. So it's probably a little easier there. We had a question that's a little complicated, regulatory question involving feds and states. Let's see how this goes. How does the concept of an open access tariff on distribution fit with the wheeling charges under PURPA, or how are they the same or different? I'm not sure if you're able to answer that question.
Not exactly to the PURPA, but I think, as I was saying before, I don't think there needs to be an open access tariff at distribution, because we already effectively have that with most of the interconnection standards and requirements under those rules that govern both, particularly for restructured states where you have wholesale distribution tariffs that the utilities have that mirror what the ISO has with respect to distributed resource participation in the market, as well as those interconnection rules and tariffs related to the interconnection of resources to the distribution system, whether behind the meter or being able to export energy across the distribution. And in restructured states, we also already have retail wheeling tariffs that exist that came 20 years plus ago with retail access. And so generally, most states have rules existing that govern or enable parties to move electricity across the distribution system. So I don't think we really need a separate open access tariff, because if you created one, you'd have to go and touch all those other tariffs and you know and resolve any potential conflicts on what you were trying to accomplish.
Thanks. Here's a question about.
By the way, I should mention this has come up in the microgrid community microgrid tariff discussion. So the work that I've been doing in California and Hawaii on these topics has brought this to bear as well, because you're dealing with the same sort of issue of exporting energy on distribution systems.
So thinking again about, we have, mostly public utility commissions in our audience today. So what roles do you think public utility commissions can play with respect to, say, data sharing, which seems like a fundamental area to tackle early on, and even absent, a framework that's, advanced in the discussion?
Well, they're really, I'm going to oversimplify here, and I'm sure Jeff has some thoughts on this as well, but there's sort of two fundamental data points that are important to start the conversation with. One is, what is the state of the resources that may be participating in the market or providing grid services and the like to the utility, those energy exporting resources in particular. So what is the state of those? How much energy are they producing? If it's a battery, what's its state? Is it charging? Is it discharging? Is it available or not? And the second is around load. What is the current state of load? Increasingly, people are talking about being able to understand the underlying load, not just the gross load, as they may call it, as opposed to just the net load. But those are really fundamentally two data points that people talk about. The question is, where do you need that information? Do you need the load at the individual meter level, or in terms of your bulk system operator, or do you just need it in aggregate form at the substation transformer on the high side, not even on the low side, right? So you need it on the transmission side, or where do you need it? What level of granularity is really appropriate? The distribution operator will have a different perspective on that because they have different needs. On the resource side, do you need it aggregated in some fashion, depending on how it's being participating in the market, or do you need down to the individual device level? Jeff, any thoughts?
Yeah, some of this really also intersects with the nature of that spectrum of models we talked about. So if you were going to gravitate toward a total TSO model, then you need to have the transmission system operator have an enormous amount of information about what's going on in distribution, because they're going to try to optimize all of that. And that's actually a little bit of a scalability issue if you think about that in terms of large penetrations of DER. And it's not clear that it's a good idea to try to do that, because then the market clearing mechanism blows up at the same time. On the other extreme, all that the TSO has to have is aggregated values at that transmission distribution interface. The DSO assembled those as aggregated values, so the information flow is actually kind of small because it's just that aggregation. In between, the hybrid models, of course, have these different trade-offs. So when you think about information sharing, you have to think about the structure in which you're going to do it, because that tells you a lot about the nature of that interface and therefore what has to be exchanged across it. So an early decision for people in thinking about this has to do with what kind of structure they want to do this in, because once you pick that, those other decisions tend to fall into place and become clearer. If you don't have a structure in mind, then it's very unclear and you end up with juggling a lot of different things. Well, it might be this, it might be that. We can't really decide because we don't know. So getting those decisions in the right order kind of helps, and getting the structural model clear up front, even if it's going to be an evolving model where you go to something hybrid first and then move in a direction, helps you think a lot about that very question about when information has to be shared.
Yeah, and that information and data, as Jeff said, it refers to that functional breakdown we talked about in terms of roles and responsibilities. That will help inform what the information that is needed and by whom and when and how frequent.
We only have about a minute left, but I thought I'd just give you an opportunity to say anything else that was in FERC Order 2222 that's going to impact this going forward. You mentioned that the order indicates that people should get together and discuss, a framework. Is there anything else in that order that you think will affect the discussion going forward?
I can't tell you that I've digested all of it yet. I knew about the suggestion because Lorenzo pointed it out to me because he went through it in some detail. I have to do more studying before I could say much more about that. It's a pretty complicated thing, as all these work orders are. So I don't have much more that I could offer right now.
Okay, well, thanks so much. I appreciated that we had a lot of the time for discussion. I think that's easier for people to get their arms around. Kerry, back to you. Thank you.
Thank you both. Your expertise is always valued here, so we really appreciate your time today with us and anytime you join us. So I think we're going to bring up Dr. Stewart. So we will see you both another time. Coming in for round 2 is Dr. Stewart. You were hearing from her earlier.
Hi there.
Hi.
How's everyone doing? I'm about to talk about a slightly different piece that I'd referred to a couple times in the first presentation. So everyone understands what I do about the structure here. I had moved some of the sensors and communication stuff out of Distribution 101 and into the beginning of cyber. And there's a really important reason for that, in that everything to do with the cybersecurity system is related to the communications and data networks. And so I wanted to make sure that basic introduction was there before we delved into things to do with cybersecurity. And again, the introduction here for cyber is mostly around what the words mean, what we talk about when we're referring to industrial control system cybersecurity, and what the components are to be thinking about when you're talking about your strategies or learning about the strategies that different utilities have put in place for the distribution system in particular. So we can get started. Next slide. So like I said, goals of this session were, and you've got me for slightly longer this time, to understand the communication system and its function within the distribution grid in particular. So primarily, again, we're talking about distribution, transmission and distribution when it comes to communications and to cyber are pretty different, actually. And for all the reasons you've heard already, that's for a reason. Then I'll give this introduction of what is cyber and what do we care about with regards to ICS, discussing the operational technology and information technology networks. And again, that's why it's important we talk about communication and the difference in the management of them and the different systems that are concerned. And then I'll talk about NIST's cybersecurity framework, along with some of the work that's been done on the different threat tiers and different types of protections. And again, it's a 45-minute introduction to cyber. But I'm a power systems engineer as well, who just happens to have delved into the world of cyber and understands it from the perspective of how the utility is working with it. And so I just wanted to make sure the goals here were definitely around the sort of understanding of words and background in the system when you're thinking about all the different sessions over the next 3 days. So next slide. So basic introduction to how we measure components in our system. How we get from the point of measurement to the point of visualization of the data. So I'm just describing this sort of picture here of where we start up with the variable you want to be measured and how it's connected to the power system. If you consider that to be a smart meter, it's connected to both the communications backhaul for the AMI network, along with the actual electrical communication or electrical connection to your house, for example. So the point of connection where it is on the power system is very important to work out how much data you need to transport and what is useful. And then there's the measurement device itself, be it earlier I was asked about inverters doing measurements, or a smart meter, or an advanced type of sensor that takes over or thousands of samples a second. The measurement device that's being used is particularly important also because of the degrees of accuracy, because you want to consider if you're wanting to run an analysis on the potential of a transformer to fail in the next 12 years, you potentially want to work with higher fidelity data. And so you need to consider also the accuracy at the point of connection as well, because everything is connected to the system generally through some form of measurement device, be that a potential transformer or a current transformer, essentially to get to that point. Then what I'll talk mostly about here is the communication system, how that works. And then there's also a case where sometimes people run local analytics and you never actually see the data, you only actually see the outcome of the data. A good example of that is actually some of the billing data that's done. That is a calculation that is done of the level of current, for example, that you're pulling into your house. And that's actually something that's sent back as a function of other components that are measured. Again, we get to the point of useful information. Everything we talk about is how to get from measured data to useful information, from which people can then take an action. And then there's a system electrical response in there. So if you take an action, for example, there's going to be a failure in the system, we need to take an action. There's then a system electrical response that happens, and a feedback loop that we're back to the variable we've measured to confirm that that action has actually taken place. So there's a pretty solid loop here of things that happen, but again, it's not generally as simple as just, we want to measure power, we stick a sensor in there and send the data back. There's a number of other pieces that are important to the system. So next slide. So again, focus here is mainly on the distribution system. Apologies, 2 seconds, I need to move my control panel out the way of my own slide. It's mostly on the distribution system and its makeup, but again, communication systems are critical throughout the system. I mentioned this is focused on distribution, but up to the level of transmission, we have numerous things that would be sent back data-wise, which use generally private networks, the SCADA system, a number of other things, and it's connected and protected in a particular way. When we get into distribution and we expand this a little to focus more on the communication system, the types of communication depends on the type of function you're actually looking for. But on a very basic level, we tend to separate protection from metering. If there's a type of measurement you need that's meant to take an action locally, like protective relays would take, you'll focus on being able to send that data within the controlled boundary that's needed for protection. But when you're talking about things like smart meter communications, you want those to go up to the higher level and billing to be sent back to the right people. So we tend to separate those protection networks from the other networks that are used in the system. So essentially, when you're standing in a substation, someone might ask you, what sort of comms are you using? And they'll say, well, this is the protection network and this is the billing or revenue metering. So then you know it's a separate measurement system. And that's both for cyber and legal and protection reasons. Does every utility have a dedicated network that they use is something I've been asked a couple of times, and the answer is some do. There's some of the more advanced utilities or people that have gone further into the world of control for the distribution system have developed their own private networks that are dedicated to that utility, and they can use that for their own functions. Otherwise, utilities can purchase communication networks from external entities. There has recently been a degree of sharing of different types of communication, and also you can have fiber lines dedicated to the utility. It can go many ways. I've done a lot of sensor installation work in the last few years, and often the first thing we're asking, well, is if we put the sensor here, how are we going to get the data back? I'm working with one just now with a large IOU. We have 2 types of sensor going into their utility. One of them captures data, I think, at a rate of 30 megahertz. And as you can imagine, sending that data back it's going to get stuck somewhere. It's too much data to really come back. So there's lots of different ways to optimize that. We wanted originally to use fiber optic, as we were going to pull a new AT&T line actually out to the substation. The cost of that ended up being significant because it was a rural utility or rural substation, sorry. And we ended up running with a 4G modem, but placing data analytics at the device so that we actually can compress and send the data in a way that doesn't just block its own communications. Because essentially, if you think of it as a pipe, at some point you can block that pipe by just sending too much information through it. So next slide. So I think I might have to click a couple times or it's frozen. I'm not sure. Oh, there it is. So the type of communication, like I said, depends on the type of functionality you need. So again, if you're planning for communications, the best, in my opinion, the place to start is what you actually want to get the data to do once you've got it back. So again, I mentioned the planning processes and roadmaps in here for things like protection versus control. The planning process there that I've done previously for sensing and measurement was what do you want that data to do and how fast you need it. Why would you pick one type or the other? Depends generally on the function. So the types of, I've given some examples here of the types of communication networks that are actually used in those different scenarios. If even up to the transmission system here, if we're talking about generation, secure wireless and radio networks can be used to transmit control monitoring messages. In some cases, those radio networks are literally people talking to each other on a radio for control, but generation generally has radio networks in place. They also use telephone service and things that are called POTS, plain old telephone service, to transmit messages between plants, because in the end you need it to be, for those kinds of systems, the most reliable solution possible. And if that's a wired telephone service, then that's what it needs to be. Consider when we have, in California, we prepare for earthquakes. So consider the fact that we're told often to keep having a wired phone service in our house just in case of an earthquake, because we can't necessarily rely on our cell phones at that point. So same theory there. In the transmission system, we're down to sort of power line carrier, which is using the power lines themselves to transmit information through a type of sensor. Substations can also use radio and wireless within their substations and communicate between the substations. Again, radio and satellite phones can actually be used during restoration and repair, depending on where you actually are. Because the point here is it's not just the devices that need to communicate and be secure, it's the humans as well. They need to actually be able to talk to each other, and that's an actual important piece of how our grid works. In distribution, recently there's been actually a lot of work going towards using fiber optics, especially for controlling load. In some cases, it's absolutely necessary to use fiber because you need the data to be as close to instantaneous between the 2 points as possible for synchronization. But yeah, again, there's been a lot of moves toward fiber, but something I mentioned earlier, transmission has, I think when people describe this, I'm never quite sure I want to say it, but transmission has 100% or more data coming back in visibility, whereas distribution, I think the last metric I had was somewhere in the 30% visibility. So the trade-off here between the cost of new sensing and the cost of communications needs to be considered when you're putting devices in place. Lastly, we're down to smart grid communications, which essentially is something I talked already, the smart meter networks, possibly control distributed generation into the DER management systems, and also the forming of wireless mesh networks between them. There's a backhaul that's used essentially for the smart meter networks, which can depend on various backbones, but again, that's one of the probably more data intensive features now of the distribution grid, is how you pull those back. And so next slide. So there's one thing that's important to talk about is also the dependency of things now on the communication system working. I mentioned the idea that if two generators, imagine two diesel generators are trying to talk to each other, they need to electrically synchronize to the 60 hertz part of the system and to each other. If they don't, there's a good chance they're probably going to kick each other off the network, and that's not the best solution. So the dependencies of the system essentially to talk to each other are pretty important. One scenario we've looked at from the prevalence of smart devices on the same network as a number of other devices was what happens if you're relying on those distribution devices to actually perform an action based on something they've sensed, but also relying on them at the same time for the billing system and relying on them to send you back information on the outage. There's some work going on here to work out how you monitor the bandwidth of the system. It hasn't really been a huge problem up till now. There's very few cases where that pipe for communications has got blocked in any way. But when you start to look at these more advanced applications around voltage control, local operation, self-healing systems, at what point do we start to get to a limitation on that? How do we visualize that? And what happens if you can't see those communications issues? So you need to be able to see the information to actually do something about it. So how do we monitor that better is kind of the future looking world. How do you plan effectively using a combination of things like distribution planning tools and communications planning tools. How do you plan effectively for your future communications needs? Not run into the same sort of world that we did with DER, and that we need to be planning much further ahead, not necessarily just for what's right in front of us. So planning for communications is a relatively new field, but it's something that's growing in importance for most of the utility environment at the moment. Next slide. So just a brief overview of the sort of timeframes I'm talking about and how you make those kinds of choices. If we are considering, this slide is from Sasha von Meyer from Berkeley. Actually, we used it when we were developing micro PMUs years ago to talk about where that sort of data sits. So synchrophasor time stamping being, which was until recently probably one of the fastest type of data you could get back in the utility environment. So the scale here we're looking at is way on the microsecond up to years and decades. So if you consider monthly customer bills, even up to planning horizons for the transmission system, which is in the years and decades. There's a wide range of things that you're measuring for and different phenomena of interest that you might be collecting. And so understanding your communications and control networks with reference to what you're actually trying to get to is the entire point of this picture. Essentially showing that if you have synchrophasors, yes, you might be able to get up to monthly customer bill, but you possibly didn't necessarily need all of that data if your only function you wanted was the customer bills to be correct. So making sure people understand their application, understand the types of things they're able to see and what they're definitely not able to see with their data is an important thing to consider. Some of the other ones are looking at harmonics and transients in the system. Doing harmonic analysis is not that fun actually, but it's something that requires a level of data and a level of accuracy and a very specialized sensor to actually do and to do it correct. And so you can make a mistake in doing a harmonic analysis of a system that can also cost tens of thousands of dollars if you don't have the right data to validate it. So just explaining the benefits of different types of phenomena and timescales and issues that they have there. So next slide. So I'm summarizing here just sort of the types of sensors you see at different levels. Grid sensors include things like current transformers and potential transformers at the basic level, phasor measurement units and micro phasor measurement units, which are measuring voltage and current, magnitude and phase angle, which gives you directional type flow information to work out deviations and things like power flow from the phase angle data. RTUs and IEDs essentially are things that are within substations, which assist the supervisory control and data acquisition system down on the left in actually creating the measurements and sending the information back to the utility. In the actual primary distribution system, and I think we've gone over what that looks like, there are things to enable the types of voltage control and fault location that I mentioned earlier, things like line sensors that are determining current flow or current spikes on the sensors. And also fault indicators, where essentially there can be conditions where even a field crew person can just see a light on a device sitting on a pole and they know that there's something faulted on that line. And so they know what to do or where to see it, because we still rely on a degree of visual interaction with these kinds of things. And then in homes and aside from the smart meter network, we also have things like environmental sensors and temperature sensors, irradiance, things that can be used to help us forecast better and control different variables in the network. So for example, when you have a 110-degree day in Livermore, we have a problem that we sometimes lose one of the transformers. And so being able to actually focus on that going on, knowing what the temperature is and knowing what you're predicting and having enough data to validate that is important for managing your load further downstream and making sure we can keep going when we need to. So next. So Kevin actually mentioned all of this in the first world when we were talking about the OMS system, the outage management system and distribution management, in that there was old versions of computers before and paper maps can still be used in some places. This is a really old picture now. I think it's 17 years old, But traditionally, the distribution operations center did work a lot by phone. They observed status, they threw switches, they did a number of things with the phone. The phone is still part of our communication system. It's just evolved a little from the rotary phone. But we have expectations of, we see all these new technologies during this kind of training, and you walk into an operations center and generally the real world is a little bit less advanced than all of the new shiny things that you see. And a lot of what we do is about making choices of where the best sort of bang for your buck is and spending in that world. And so at the moment, even if there's a home or a place that does not have smart meter technology, often one of the first ways the utility does know there's a problem is when that customer calls in. That's still a system that exists. Customers do still need to call and say that they don't have power in some cases. Living in California, we've had obviously more incident of that than not. As it turns out, the utility knows most of the time when they turn off our power. But the customers still call in, and other things like power quality issues are interesting there, that a lot of the time a power quality sensor is measuring a waveform, which is something you don't necessarily want to push through your communications network. So that waveform isn't that common to get from a few locations. I just did a project where I carried back about a day of waveform data, and it took a full hard drive to bring it back with me. And yes, I was hand carrying data back with me because I didn't really have a way to send it through our network. So power quality issues are in that scale where it's down on that left-hand side of the graph I showed you, and getting that data back through a communications network is a challenge. And so a lot of the time, the way that people know there's a power quality problem, which is generally something like your lights are flickering in your house, is again, people calling in and still communicating that they have a flickering light, for example. Gradually, on the next slide, sorry, SCADA has been introduced to the distribution system. I mentioned earlier the D-SCADA type world, which gives the operators the ability to observe the status of the field equipment through these remote terminal units. SCADA platform, as I said, heart of the utility operations environment. Originally, D-SCADA and transmission SCADA together were sort of coupled together in the system, making sure that we, and sorry, if you could move the slide on one, that'd be helpful. Thanks. D-SCADA and transmission SCADA together were, oh, sorry, one more slide as well, were scoped together because it was, gave the sort of lowest cost to acquire, to operate and maintain the consolidated network as a secure platform for both the transmission operator and the distribution operator. There was a common infrastructure between them both. So it gave the lowest training requirements also because they could work together and putting that in place. Sorry, one more slide. The negatives of that were changes to the distribution portion of it were causing frequent changes to the transmission portion of it. And the structure of SCADA, essentially I'd mentioned, again, this is the more detailed version of the very first picture you saw, where we have your sensors with the measuring physical qualities, the RTUs performing the conversion of the data, the telemetry actually communicating the information, and where they collect the information and do the analysis. So next slide. We can go on a couple, sorry. Okay, so talking through the smart meter networks a little more, and I want to make sure I get to the actual cyber slides because I realize I've taken a little longer than I planned. I think I already described AMI to a degree, but the backbone of AMI is also this communications network. And there's a rate of adoption depending on the different regulatory incentives and understanding what the benefit of them is. Next slide. And I've probably covered most of these, so we can probably step on. I think I carried them in the first one. So that was my first piece. I wanted to describe what we're communicating and why. The second part of this was where I wanted to talk about cyber and give this introduction to the cybersecurity environment. So what do we care about, and what do some of the words actually mean in this environment? So this picture here is a public picture that's well publicized about the number of cyber attacks we've had in the US over the number of years. For everyone's, Ukraine was one of the well publicized attacks, which really showed us that attacks on infrastructure that have a physical impact are no longer really theoretical. But there's some other good examples that have happened in the US. I think it's the Bowman Dam was one of the ones that were interesting because, as it turns out, we believe that that was an attack on a dam that was the wrong dam because it shared a name with another much larger situation. But the name's wrong dam, but good try was the thing that people said. An airport was a teenager, I think Massachusetts airport, and would include a teenager managing to break into systems. And then we move forward to one of the more recent issues, which includes the Triton attack, which was probably one of the first examples in the US that we'd seen where loss of human life was considered an actual acceptable outcome to that event, which is an unfortunate big step forward in what we look at in these systems. So there's a big difference here between a ransomware attack, where there isn't necessarily always a risk to human life. There's a risk to business systems. Stepping up to an actual attack on control systems that could have an intentional or unintentional consequence of the loss of human life. So the scale of things has been increasing over time. So if we step through, I forgot those pictures were there, sorry. We step through to the next one. So Dan Coates, former Director of Natural Intelligence, had given a public discussion testimony about a year ago, or I think it's 2 years ago now, on the capabilities and intents of Russia and China to map our infrastructure. Similarly, everyone's probably heard about the election system worries, and the scale of attacks are growing. And so it's something we need to be more intelligent about and more intentional on how we manage those cyber physical systems. And so on the transmission side, there's been a lot of work on how that's done, because transmission is obviously the bulk system. It's a much a small attack is a much larger impact. But as we start to link together distribution system controls, operational systems, ADMS, as I talked about, we need to consider the bulk impact of the distribution system and how to both get all of the benefits from the distribution components while also not slowing down their ability to be deployed, but also protecting the critical infrastructure from potential adverse impacts of those attacks. So taking a bit of a step back to the basics, next slide, sorry. If we think about cyber, like I said, we need to think about communication system. There's a large difference between an intrusion into the industrial control system versus the IT network. And there are rules in place for how those two are not meant to be connected, but in many cases, there's still ways that happens. And also considering things like malware versus lockouts versus control disruption to the system needs to be seen on different scales of how we must work with it. So next slide. So I mentioned IT and OT. Almost everything I've talked about today is all on the OT side. We can't deal with them on the same level. IT does include a lot of business systems. It is critical to managing data, but it's not generally where the real-time sensing systems live. It's not where operational systems live. The types of things that are seen here a lot are to do with ransomware, locking people out of systems. But again, the availability of the system is generally not as critical, and you can reboot without losing control of a device or taking it offline entirely. Where what does live in the IT network is part of the AMI network, which is to do with customer privacy and human privacy. And all those kinds of items are sitting in the IT network. So depending on what your biggest concern is, IT is either the most critical thing or it's lesser than the OT network. So it depends on what you're worried about. If human privacy, for example, in the medical field, is the number one worry, then IT is your priority. If you're worried about control processes, that's where OT lives. So OT network manages physical as it sounds like things that are used for operations. Priorities are generally safety, continuity, and fault tolerance. It's real-time systems that are working with here. Again, human safety is always kind of the paramount thing that everyone considers first. The systems are often diverse in the OT network. They're often proprietary as well. And software updates typically need to be done through the vendor. So if you consider things like distributed resources, you probably have an inverter in your house that is developed by one vendor. And then there's another device that's talking to it that's developed by another vendor. the vendors generally control how those updates happen. You have to communicate to their network to get new firmware. And so it can be a complicated interaction of systems, and that's where interoperability becomes critical. And also OT networks can be isolated. You want to isolate your OT network, but pieces of it can be isolated in different places. So often recently, and why we're talking about this is and especially around the distribution system recently, a lot of the IT ideas of how you secure a network are being applied to the OT network and are not generally actually adapted to the requirements of the system. So there's a lot of new thinking that needs to happen about that control. So talking a little bit about the frameworks we use on the next slide, NIST, or the National Institute for Standards and Technology, I tend to get the S wrong. They developed a framework to help infrastructure and industry understand the needs they have for cyber. And in this framework, they talk about different classes of protection, which include identify, protect, detect, respond, recover. These 5 classes are essentially meaning to help you understand what protections you need to put in place for that different type of event, or what the different functions are in each world. So if we step through it, identify is actually the planning step. So knowing, and sorry if you could move to the next slide, knowing what you actually have and what your risk is. So we say know thyself. So identify what your actual assets are, your data, the people that are attached to it and using it, and also understanding how your network behaves, so you actually know when it's not behaving the right way. So if you suddenly have a flood of data coming in from your smart meters, for example, then is that normal? Did something actually happen that caused that? For example, there was a large event was happening and everyone had an event that got sent back all at the same time. That's one thing. That all happening without an event related is another. So understanding how your network actually behaves is a critical piece. And also understanding what you're defending against. So the risk that you're at, identifying where the vulnerabilities are and the potential impact. And so the categories of work that go into this include sort of risk assessment and management, business environments, looking at asset management, understanding what's there, knowing how it works, and you can't defend if you don't know what's actually on your system. So another one that people may have heard about recently is the supply chain risk management as well. That's where this falls into identifying what you have on your system and how it's being used. So next slide. So protection of your system is essentially at the very basic level, nothing is actually perfect. Protection does make it harder though for people to get into the system, and at a basic level this is where you have things like encryption, network segregation and segmentation, which is where when people say IT and OT must be separated, that's where this is. Authenticating users, so people being able to, when we talk about double authentication on systems, authenticating is actually a very good way to stop people getting into your system. Maintaining an incident response plan and recovery plan means that once something happens, you actually know what to do about it. So it's all about planning for these kinds of events. Also in protection, you can reduce the attack surface and make sure you're actually up to date on devices, because I know I ignore updates on my computer quite frequently. Imagine the whole utility was doing that, because sometimes those updates are disruptive and annoying. So making sure you are patching your systems and looking for those vulnerabilities are important. So in the protect world, we have things like information protection processes, data security, actual training, making sure staff know what to do is pretty critical. Identity management, again, being a big one, and other protective technologies in here. There's no system that's perfect. There's no system that is 100% impenetrable. But there's always a human factor in lots of ways. But the objective here is to make it much harder for an adversary to get into the network. So next, sorry. So kind of like you have an immune system, knowing what you actually have happening is one of the keys to actually fighting it, assuming you're going to get infected. So how do you actually, and that's probably not the best way to put it at the moment, given what's been going on, but assume that your system is going to catch something. Assume you've got it. What do you do when someone has got into the system? Well, the best thing to do is to find it quickly and respond to it. So again, this is back to establishing your baseline behavior, keeping libraries of known events, monitoring for unauthorized connections and being able to find those vulnerabilities, but also reporting. It's kind of important here that you allow others to benefit from your experience. So when you're reporting, there's incident response people all over the globe of response, including even sort of Army Cyber Command, for example. They have processes in place for large-scale incidents that involve utilities. So making sure small incidents are reported is how those things get prevented. So detecting anomalies on your system, continuous monitoring and processes. So again, I'm not trying to say this to sound scary, but people will find a way to get into a system, but catching them quickly is a way to prevent things from spreading. So next. So one of the last things we talk about is response and recovery. Again, response is all about mitigation, sharing information, for example, through CISA, CISA, sorry. They're the nation's risk advisor, the US risk advisor for these kinds of systems, ran through DHS. Being able to do root cause analysis, if you found something new in your system, reporting it, forensic analysis on the larger system, and then being able to mitigate those new vulnerabilities that you've identified. And where this is kind of important in response is also when you consider things like inverters and DER. There's a whole bunch of new issues that are coming into play here. And so responding to new issues and being able to have an accurate, what are you going to do if this happens, is really important. So next. Lastly, we have recovery. It can take a while. One of the programs going on just now with DARPA is all about how a utility would recover from a 30-day outage that was caused by a large-scale cyber attack. And a lot of what they've learned in here is about the recovery plan more so than the actual everything else that happened up to that point. Power people and cyber people working together is one of the big targets here. And so it can be time consuming, but at some point, for example, if you're cleaning up a substation after an event, your cyber team need to come in, but they also safely need to be able to talk to the different systems in there. They need to be able to pull out what's happened, forensically analyze it, and then help clean up the system before the power gets switched back on, for example. So you can imagine that turning on power to a device that has been compromised is not necessarily the smartest thing to do because it may irrecoverably damage the system. So making sure all the activities up to this point are performed, but they're always having a plan in place for recovering, what you're going to improve after that point, and what the communication system will look like following the event that's happened. So it's a step-through process, but there's work going on in all areas to understand. On the next slide, there are some common, like the simplest thing is there's a lot of common intrusion paths that it's not actually always the most complicated way that you think is happening. It's not generally always, it can be a kid sitting in a basement as opposed to whatever else you think is happening outside in the outside world. Everything to do with sort of stealing passwords. Password strength is pretty important. Leaving things like admin and root on your system is probably not the best plan, but you'd be surprised how often that actually is the case. Being able to make sure the OT and IT networks are not connected. One recent event was Pi Historian, which is a data collection system, became a path between the OT and IT network, and making sure those were separated was actually a critical thing that had to be done. Mobile media and internet, being able to actually know what should not be talking to what within the devices and places. And also even things like phishing emails, exploits of connections, accidental things that happen, just understanding where those different pivots that can come deeper into the industrial control system. Again, this is where all the planning is important. Understanding where those pivots can happen is your first big step to actually fix it. So getting deeper into the network is key for getting up to those large scale events. So preventing that from happening starts at the very basic level where you access credentials are stolen or internet to internet devices have happened. So next slide. So defense in depth, I think, is the next slide, and it's a common term that's used, which is a combination of all these reports. And I'll just say this very quickly, that defense in depth is essentially protecting the system from the inside out. And so making sure that all these layers are addressed from down to the single component level up to the systems level analysis. So last couple slides. So who does what? What do we care about? What is typical and new types of response capability that are coming about? The Defence Science Board also put together a guide of what different scales of adversaries are. So when someone's talking to you about an adversary and they're saying tiers, it's coming from this Defence Science Board world, where adversary tier 1 and 2 are essentially people that can use vulnerabilities that are known. So when you hear that there's a vulnerability in your printer, for example, the type of people that would use that are adversary tier 1 and 2. 3 and 4 are people that can discover new ones. So the people that have found that vulnerability and then used it are 3 and 4. And 5 and 6 is up to the nation state type level where creating vulnerabilities is possible. So stepping to the next slide. And I think this is just an example of the sort of work we're doing at the moment. Adversary tier 1 and 2 is actually generally mitigated by basic cyber hygiene, antivirus, and pre-planning for events. It's not something that necessarily you need advanced research on. All of the rules that you see in place of how you work with your computers are where that's actually happening. But when we move up to sort of 3 and 4 and 5 and 6, that's where there's actually a degree of work that needs to go on and coordination between government entities. People like the National Guard are trained in some of the 5 and 6 responses, for example. So as we step through these, there's different levels, and I think that the things in light white, which I'm not sure my next slide actually had them highlighted, the things that are here are talking about the sort of work that the national labs, DHS, DOD, and DOE are doing to essentially mitigate those bigger adversary tiers that we don't have necessarily as much protection against from the basic industry level. So you can go buy an antivirus and it is very effective, but there isn't necessarily a protection that is developed presently for some of the higher tier adversaries because they're creating that vulnerability themselves. So next slide, or next couple. So yeah, we have industry and then areas where utility and industries are working together. And then lastly, the last tier, if you click the thing, is where people like the national labs are working as well. So lastly here, I included sort of the 6 strategies that the DHS National Cyber Incident Command, I think is that acronym. It's also below in the slide if you want to take a look, where they had recommended strategies for utilities and for looking at, was partially where we started to talk about the distribution system, which is where NARUC SIP isn't necessarily always used. And so some strategies here just to give some advice on where we're at and what's useful for as a very first basic level of cyber defense for the system. So I think I have included on the last slide potentially some links. There's numerous guidelines and best practices where there's starting to be new developments in the distribution system, but that is me for today. So I hope that didn't bamboozle too many people. I'm happy to take questions for a little bit.
Thanks, Dr. Stewart. Yes, please send in your questions. I am going to send out the survey for the evaluation, but I do have one question from earlier. It reads, and I think that this has come up in other trainings, but do you think who do you think is going to be responsible for cybersecurity of DERs and inverters specifically?
That's a very good question. It depends. Again, I always say that, but it does depend on who actually owns the system. Ultimately, if your system is meant to be participating in utility control, then you should be installing a system that the utility has said meets their standard for cybersecurity. That doesn't necessarily mean that's how that's happening at the moment, but there's a lot of work going into sort of the regulations and standards for what that actually means. When you're working with one of the things that the ISOs have talked about is the use of aggregators for performing in their particular, in the actual dispatch schemes there as well. And that's when sort of the aggregator is the one that's meant to meet the requirements, but then there's the individual devices and they have their own homes and people need to be held to a standard for updating those as well. So there's kind of a mix of ownership concerns that are going on, and that's actually one of the things that I think can slow down that as well. If there isn't a standard to meet, then it will never get to the level of penetration that we're hoping for in future, I think. So it is an area for future work, as well as understanding who wants what. The actual device manufacturers also are responsible for making sure their devices, if you do everything they say, are not easily hackable. So at that level, they're the ones that need to be doing that. But again, there's everyone kind of has a responsibility in this, because the device not having a vulnerability, the owner actually updating the device, the aggregator not having a hole in their just like sort of communication pathway, and the ISO themselves securing that data and that control. So it's it's kind of a mixed bag, but it's an interesting.
Thank you. Well, thank you. I'm going to just check in with Lisa Schwartz to see if she had any other closing remarks, but we will say goodbye for Dr. Stewart, and we will, and thank you so much for your expertise. And Dr. Stewart, I really love all of your personal stories. They really round out the full presentation, so I really appreciated those.
Thank you.
Thanks, Emma. Thanks, Kerry.
Lisa, did you have additional?
No, thanks everybody for participating today. Don't forget to fill out your survey. Kerry put the link in the chat box. We have a separate survey for each day, and it's really important to get as high participation rate in that as we can. Thank you.
Thank you all. We will see you tomorrow at the same time, same place. See you then.